Hello there and welcome to Science for Sleep, where curiosity gets comfortable, the universe lowers its voice a little, and even the most enormous ideas are allowed to arrive slowly, like sunlight crossing a quiet room in the late afternoon. Tonight, we're going to spend some time with a thought that sounds almost too strange to be useful, almost too large to fit inside an ordinary human evening, and yet it comes from real physics, real astronomy, and a very patient kind of engineering imagination. The thought is this: one day, humanity may use the sun itself as the greatest telescope ever built. Not a telescope beside the sun, not a telescope looking at the sun, and not a shiny golden observatory parked politely near Earth, but the sun as the telescope. Our own star, the warm, familiar ball that rises over gardens, oceans, rooftops, traffic lights, laundry lines and sleepy cats on windowsills, could become a natural lens so powerful that it might help us see the surfaces of planets around other stars. That is a rather big claim for something we usually think of as the reason we need sunglasses. The sun already has several jobs. It keeps Earth warm, drives our weather, feeds plants through photosynthesis, gives us sunsets, ruins unprotected chocolate, and occasionally reminds us that leaving a car parked in summer was not our finest decision. But hidden inside Einstein's theory of gravity is another role for the sun, a role so unusual that it almost feels like a secret feature of the universe. Gravity does not only pull planets into orbit, gravity can also bend light. And because the sun is massive, its gravity bends the light from distant objects passing near it. That bending can act like a lens, a strange, enormous, invisible lens made not of glass, but of curved space. Before we drift too far into that idea, I would love to ask you something simple. Where are you listening from tonight? Are you somewhere under a clear sky, where the stars are visible between rooftops or trees? Are you in a city where the night sky is mostly hidden behind lamps and windows? Or are you listening during the day, with the real sun somewhere outside, shining away without any idea that we are about to imagine using it as a telescope? And what time is it where you are? Morning, evening, the soft middle of the night, or one of those odd hours when the world feels paused, and even the refrigerator seems to hum more thoughtfully than usual? If this kind of slow journey through science helps you relax, settle down, or keep company with your thoughts at the end of a long day, I would be grateful if you liked the video and subscribed. It helps this little quiet corner of the internet reach more people who enjoy the universe at a gentle pace. And as always, I hope the story is interesting enough to make you curious, but not so dramatic that it makes you sit bolt upright and begin calculating orbital mechanics at 3 a.m. There is a time for that, of course, but it is usually after breakfast. So, settle in, let your shoulders drop, and imagine Earth as it really is from far away. A small blue world wrapped in clouds turning under a yellow star. Somewhere beyond us, around other suns, there may be worlds with oceans, winds, ice, storms, deserts, volcanoes, perhaps even life. We have already found thousands of exoplanets, planets orbiting stars beyond our solar system. Some are huge gas giants roasting close to their stars. Some are small rocky worlds. Some orbit in regions where liquid water could possibly exist. But for all our discoveries, for all our telescopes and data and clever methods, most of these planets are still not real pictures to us. They are dips in starlight, tiny shifts in motion, faint traces and spectra, brief shadows crossing distant suns. We know they are there, but we usually cannot see them as places. That is one of the great frustrations of modern astronomy. We can detect a planet hundreds or thousands of light years away, estimate its size, measure its orbit, sometimes guess what gases are in its atmosphere, and yet the planet itself remains almost completely hidden. It is not a world with coastlines and clouds in our images. It is a point, a signal, a whisper. Even nearby exoplanets, the ones that stir the imagination most strongly, are incredibly difficult to image directly. A planet is dim, its star is bright, and the distance between them from our point of view is tiny. It is like trying to see a firefly next to a searchlight from another country, except the firefly is not being especially cooperative and the searchlight is a star. Our best telescopes are astonishing machines. The Hubble Space Telescope changed how generations pictured the cosmos. The James Webb Space Telescope opened new windows into infrared light and has looked into the atmospheres of distant planets. Ground-based observatories with giant mirrors and adaptive optics can sharpen the sky in ways that would have seemed impossible not so long ago. Future telescopes may be even larger, even more sensitive, and even better at separating faint planets from the glare of their stars. But there is a hard problem. To see fine detail on an Earth-sized planet around another star, to make out something like continents or oceans, you would need a telescope with a mirror of absurd size. Not just big by human standards, not just larger than a stadium or a city. Depending on the target and the detail desired, you start needing something so large that building it as a normal physical telescope becomes less like engineering and more like asking the moon to hold a magnifying glass. This is where the sun quietly enters the story, not as a light source this time, but as a tool. Einstein showed that mass curves space-time, and light follows that curve. In 1919, during a famous solar eclipse, astronomers measured starlight bending around the sun, helping confirm general relativity and making Einstein a household name, which is not bad for a theory that also makes clocks behave differently depending on height and speed. The same bending that shifted the apparent positions of stars during an eclipse is the foundation of gravitational lensing. Across the universe, galaxies and clusters of galaxies bend and magnify the light of objects behind them. Astronomers use these natural lenses all the time to study distant galaxies that would otherwise be too faint. Space, very politely, sometimes provides its own telescope. The sun can do something similar, though on a scale that requires a very long walk. If light from a distant planet passes near the sun's gravity bends that light inward. Far behind the sun, along a line extending outward from the opposite side, those bent rays begin to focus, not at one tidy little point, like a school magnifying glass burning a leaf, but along a long focal line beginning at roughly 550 times the distance from Earth to the sun. That distance is called 550 astronomical units, or 550 AU. 1 astronomical unit is the average distance between Earth and the Sun, about 150 million kilometers. So 550 astronomical units is very, very far away. It is far beyond Pluto. It is far beyond where most of our spacecraft have ever travelled. It is out in the deep, cold outskirts of the solar system, where sunlight is thin, radio signals take a long time to get home, and any passing comet probably looks at you as if to say, "You're a bit far from the neighbourhood, aren't you?" To use the sun as a gravitational telescope, a spacecraft would need to travel to that distant region and line itself up so that the sun sits between the spacecraft and the target exoplanet. From that position, the light of the distant planet would be bent around the sun and appear as a thin ring of light around it, known as an Einstein ring. The spacecraft would not simply snap one ordinary photograph and receive a beautiful full-colour globe, ready for framing. The universe rarely gives out high-resolution alien planet portraits in one click. Instead, the information would be smeared and mixed by the lensing process. The planet's light would be wrapped around the sun in a complicated way. The spacecraft would need to move through the projected image region, measuring tiny changes in brightness and colour, gathering data piece by piece, then using mathematics to reconstruct what the planet looks like. In a way, it would be less like pointing a camera at a landscape and more like feeling the shape of a sculpture in the dark, one small patch at a time, then slowly building a picture from touch. That may sound clumsy, but the reward could be extraordinary. A solar gravitational lens mission could, in principle, create a multi-pixel image of an exoplanet with detail far beyond anything we can currently dream of with normal telescopes. Not a pale dot, not a tiny blur, a world, a real world. Perhaps a planet like Proxima Centauri b if conditions and geometry allowed, or another nearby rocky planet discovered in the coming decades. We might see whether it has bright clouds, dark oceans, polar ice, broad deserts, greenish or brownish regions, seasonal changes, or strange weather patterns that do not resemble anything on Earth. That last part is worth sitting with for a moment. Imagine the first image of another Earth-sized planet that is not just a dot. Not an artist's impression. Not a computer graphic based on hopeful guesses. An actual reconstructed image made from photons that left that world years ago, crossed interstellar space, curved around our sun, and arrived at a little human-built spacecraft waiting in the dark. Those photons might have bounced off an ocean on a morning we will never visit. They might have passed through clouds over mountains we will never climb. They might have reflected from ice caps, storm bands, volcanic plains, or maybe from something that would make everyone on Earth go very quiet for a while. Of course, it is important not to rush ahead too quickly. Alien cities, if they exist, are not something we should expect to spot easily just because we have a clever lens. Science has to move carefully. A bright pattern on the night side of a distant planet could be technology, or it could be lightning, auroras, reflection, noise, or 1,000 things nobody has thought of yet. The universe is very good at giving us interesting results and then waiting patiently while we embarrass ourselves with overconfident explanations. Still, the possibility is there in the broader idea. A telescope powerful enough to distinguish large surface features might someday help us search for signs of life or technology in a way that feels more direct than almost anything we can do today. We would not only be asking, is there a planet there? We would be asking, what kind of place is it? That question changes the emotional shape of astronomy. For a long time, planets around other stars were only guesses. Then they became detections. Then they became statistics. Now we talk about atmospheres, habitability and biosignatures. But seeing one as a place would be another step entirely. Humans are visual creatures. We can read a table of data and understand it intellectually, but an image can land differently. The first photograph of Earth from space helped change how many people thought about our planet. The pale blue dot image from Voyager showed Earth as a tiny speck in a sunbeam and made our home feel fragile and shared. Imagine a future image that does something similar, but for another world. A small disk, perhaps cloudy and blue, or copper-coloured and stormy, or covered in patterns we do not recognise. It might not answer the question of whether we are alone, but it would make the question feel less distant. The journey to build such a telescope would also change how we explore our own solar system. Sending spacecraft to 550 astronomical units or beyond is not a casual mission. Voyager 1, one of humanity's farthest travellers, has spent decades moving outward and is still nowhere near that distance. A solar gravitational lens mission would need to move much faster. That is why many concepts involve small spacecraft, lightweight designs, and solar sails. A solar sail is a thin reflective sheet that uses the pressure of sunlight to accelerate. Sunlight may feel weightless on your face, but photons carry momentum. If you give them a large, light surface to push against, they can move a spacecraft. Slowly at first, then steadily. Some concepts imagine sending spacecraft inward toward the sun, diving close to it, unfurling a sail, and using intense sunlight to gain enormous speed outward. It sounds like something from a patient, well-funded space fairy tale, but the physics is real, and the engineering is the difficult part. There is something charming about that. To use the sun as a telescope, we might first use sunlight as the wind. We would sail toward the star, then away from it, carried by the very light that later helps us study other worlds. No roaring engine in the usual sense, no highway, no service stations, no little sign saying last coffee before the Kuiper belt. Just a small machine, a reflective sail, careful navigation, and a long outward fall into the dark. It is one of those ideas that makes the solar system feel both huge and strangely usable. The sun becomes not only our star, but also our lens, our launch assistant, and perhaps one day our signal booster. That signal booster idea is another part of the story, and it stretches even farther into the future. If stars can focus light, perhaps they can also help focus communication signals. A civilization that learns to use gravitational lensing might build communication links across interstellar distances, using stars as natural amplifiers. Some researchers and writers have imagined a kind of galactic internet, not made of cables or satellites in the ordinary way, but of carefully placed probes using stellar gravitational lenses to send and receive faint signals across the galaxy. It is a very speculative idea, and it belongs to the future more than the present, but it follows from the same principle. Gravity shapes the paths of light and electromagnetic waves. A star is not only a lamp in the sky, it is also a massive object that bends the geometry around it. A patient enough civilization might learn to use that geometry. For now, though, the dream begins with a much simpler wish. We want to see. That is the oldest wish in astronomy. We looked up and wanted to know what the lights were. We made lenses and saw moons around Jupiter. We built bigger instruments and found galaxies beyond the Milky Way. We launched telescopes into space and saw nurseries of stars, disks around young suns, storms on distant planets, and galaxies whose light began travelling before Earth had animals walking on land. Each time our tools improved, the universe became more detailed. Not necessarily smaller or simpler, usually the opposite. More complex, more surprising, more full of things that had been there all along, waiting for our eyes to become good enough. The solar gravitational lens is part of that same long tradition, but it asks us to stop thinking of a telescope as only something we build. Sometimes a telescope can be something we find. A galaxy cluster can be a telescope. A black hole can create lensing effects. The sun, sitting at the centre of our ordinary days, could be a telescope too. It has been there for 4.6 billion years, shining, bending light, holding planets in orbit, and quietly offering a method we could not understand until general relativity gave us the language for it. The tool existed before the toolmaker knew what it was. That does not make the mission easy. It may take decades of development, and perhaps decades of travel. It would require extreme navigation, clever instruments, a way to block the sun's bright corona, reliable communication across hundreds of astronomical units, and software capable of reconstructing an image from distorted light. It would require choosing the right target, maintaining alignment, and being comfortable with a spacecraft so far away that even messages moving at light speed would take days to travel back and forth. Every part of it is difficult, but difficult is not the same as impossible. Much of space exploration lives in that gap. The gap between what sounds absurd and what becomes normal after enough patient work. Think of how strange it would have sounded not so long ago to say that humans would place a telescope beyond Earth's atmosphere and use it to watch galaxies forming, or send robotic explorers to Mars, or land a probe on Titan, or measure ripples in space-time from colliding black holes. Science often begins as a sentence that feels too large for the room. Then someone does the math. Someone else builds an instrument. Someone argues about funding. Someone tests a component in a vacuum chamber. Years pass, more years pass. A launch happens. Something unfolds in space. A signal comes back, and suddenly the impossible has a project page, a mission team, a data archive, and a slightly blurry press conference image that makes everyone cry anyway. The sun becoming the greatest telescope ever built is one of those ideas. It sits at the edge of our current ability, looking back at us with a calm expression, as if it has all the time in the world, and in a sense it does. The sun is not in a hurry. It has been bending light since long before there were humans to notice. It will continue to bend light long after tonight's worries have become small and manageable. Our task is not to make the sun powerful. It already is. Our task is to learn how to stand in the right place with the right instrument and listen to what its gravity is already doing. When we talk about planets beyond our solar system, it is easy for the imagination to get ahead of the images. We hear that astronomers have found a rocky world around another star, or a warm planet in a possible habitable zone, or a giant world with strange clouds, and the mind immediately begins painting a scene. There might be blue oceans, there might be rust-coloured deserts, there might be white storms curling over an alien hemisphere, there might be dark volcanic plains, frozen poles, thick orange haze, or a sunset where two moons hang over a sea no human has ever seen. The mind is very good at this. Give it one sentence about a planet and it starts building coastlines. It adds wind, it adds weather, it adds a little mountain range in the distance just for atmosphere. But the real images we have, the actual direct views of most alien worlds, are not like that at all. They're usually not globes, they're not landscapes, they're not photographs with clouds and continents and a charming little arrow saying, "Possible beach here." Most of the time, they're not even pictures of the planet itself. They are measurements, shadows, tiny movements, changes in light, small signals hidden inside the overwhelming brightness of a star. This is not because astronomers lack ambition. Astronomers are some of the most patient people on Earth, which is saying something, because they regularly spend years trying to understand a dot that appears in 3 pixels and then write a paper about it with great seriousness. The problem is physical. Planets are small compared with stars. Planets are dim compared with stars. Planets are close to their stars, at least from our distant point of view. And space is so large that even a nearby planetary system is not nearby in the everyday sense. It is nearby in the astronomical sense, which means it is still so far away that if you tried to describe the distance during a normal conversation, people would begin quietly checking whether there was more tea. Think about the nearest star system to the Sun, Alpha Centauri, and within that larger system, Proxima Centauri, the small red dwarf that hosts the famous planet Proxima Centauri b. Proxima Centauri is about 4.2 light-years away. That sounds short because the number is small. 4.2, very manageable. You could have 4.2 biscuits, if you were being precise and slightly alarming. But a light-year is the distance light travels in 1 year, and light is not known for taking a leisurely stroll. It travels about 300,000 kilometers every second. So even our nearest stellar neighbor is tens of trillions of kilometers away. The planet around it, from our view, is tucked extremely close to the star. Not physically close in the sense of being inside it, of course, but visually close, like a candle flame beside a lighthouse seen from miles away. That is the first reason alien worlds remain blurry, or even invisible to us. A telescope does not only need to collect light, it also needs to separate things. Astronomers call this angular resolution. Imagine holding your thumb up at arm's length and trying to cover a distant street lamp. Your thumb and the lamp seem close together in your field of view, even though they are at very different distances. Now imagine trying to separate a planet from its star when both are so far away that the distance between them appears smaller than the tiniest gap your eyes could ever notice. A planet may orbit millions or hundreds of millions of kilometers from its star, but from many light years away, that separation shrinks into an almost impossible angle. It is not that the planet has vanished, it is that the universe has compressed the scene into a tiny patch of sky. Then comes the second problem, and it is even more unfriendly. Stars are bright, very bright. It sounds obvious, but in exoplanet imaging it becomes the central nuisance. A star is a self-luminous furnace. It makes its own light through nuclear fusion. A planet, unless it is very young and still glowing with leftover heat, mostly reflects the light of its star or emits weak infrared warmth. Compared with the star, it is faint almost beyond politeness. NASA explains that planets can be billions of times dimmer than their host stars, which is why they're usually lost in the glare. Trying to directly image an exoplanet can be like trying to see a firefly beside a spotlight, except the spotlight is not across the garden. It is across interstellar space. This is why many exoplanets are not found by taking their picture. They are found indirectly. One of the most successful methods is the transit method. If a planet passes in front of its star from our point of view, it blocks a tiny fraction of the starlight. The star dims just a little for a little while. If that dimming happens again and again on a regular schedule, astronomers can infer that a planet is orbiting there. This is how missions like Kepler found thousands of candidate worlds. It is a brilliant method, but it gives us a shadow, not a portrait. It tells us the planet exists. It can tell us the planet's size, orbit, and sometimes clues about its atmosphere if starlight filters through the atmosphere during the transit. But it does not show us the planet's surface. It is more like noticing someone walked past a lamp because the room got slightly darker for a moment. Another method is radial velocity. A planet's gravity tugs on its star, not enough to throw the star around dramatically unless the planet is huge and close, but enough to make the star wobble slightly. That wobble shifts the star's light toward blue and red as it moves toward and away from us. Astronomers can read those shifts and infer the presence of a planet. Again, this is wonderfully clever. It is like learning there is a small child pulling on the sleeve of a giant by watching the giant sway almost imperceptibly from across a field. But it still does not give us a picture of the child, or in this case, the planet. It gives us mass, orbit, timing, and evidence. It gives us science. It does not give us a map. There is also microlensing, where the gravity of a star and planet can briefly magnify the light of a more distant background star. There is astrometry, where astronomers track tiny shifts in a star's position on the sky caused by orbiting companions. There are timing variations and other methods that sound, at first, like someone solving a mystery with only the faintest creak from the floorboards. This is what exoplanet science has often been. A detective story told through missing light, bending light, wobbling stars, and patterns that repeat if you watch long enough. It is remarkable. It is also a reminder of how hidden these worlds are. Direct imaging does exist, and it is one of the most exciting parts of the field. Astronomers have directly imaged some exoplanets, especially large young gas giants orbiting far from their stars. Young giant planets still glow with heat from formation, especially in infrared light, and if they orbit far enough from the star, a telescope has a better chance of separating them from the glare. Instruments can use coronagraphs, which block the star's light inside the telescope, or other methods to suppress the glare. This is a bit like holding up your hand to block the sun so you can see a bird flying nearby. Except the hand must be impossibly precise. The bird is faint, and the sun is a star many light years away. Direct imaging works best in special situations, especially with young nearby systems where the planets are bright and widely separated. The images we get from direct imaging are scientifically valuable, but they are not what the imagination wants them to be. They often show a star's light blocked out, with small points nearby that mark the planets. The famous HR 8799 system, for example, has multiple directly imaged giant planets, and it is extraordinary to watch their orbits over time. But those planets are not detailed worlds in the images. They are points, important points, real points, points that changed astronomy, but still points. Even when we directly image a planet, we're usually not seeing a disk with features. We are seeing a faint dot separated from a much brighter source. That word, dot, may sound disappointing, but it should not. A dot can be a triumph. A dot can represent years of work, careful calibration, nights of observing, instrument teams, data processing, and the quiet persistence of people who know that the universe does not have to make things easy for us. A dot can tell us colour. It can tell us brightness. If we split its light into a spectrum, it can tell us about gases in the atmosphere. It can suggest temperature, clouds, chemistry, and sometimes formation history. A dot is not nothing. A dot is a door with the lights off behind it. Still, the reason this story matters is that a dot is not enough if we want to understand alien planets as places. For that, we need resolution. We need multiple pixels across the planet's face. One pixel cannot show a continent. One pixel cannot show whether the bright area is ice or cloud. One pixel cannot show a storm moving across a sea. If Earth were seen as a single pixel from far away, it would change in brightness and colour as it rotated. A very clever civilization might infer oceans, clouds, vegetation, maybe even a day length from those changes. But they would not see Africa. They would not see the Pacific. They would not see the swirl of a hurricane or the white cap of Antarctica. Earth would be a tiny changing sparkle, full of information but stripped of shape. Astronomers can do a great deal with that kind of sparkle. By measuring how a planet's brightness changes as it rotates, scientists can sometimes infer whether it has contrasting surface regions. By studying spectra, they can search for molecules like water vapor, carbon dioxide, methane, oxygen, or ozone. Future telescopes may look for combinations of gases that could suggest biological activity. This is one of the great hopes of exoplanet science, to detect signs that a distant world is alive without needing a picture of its forests or oceans. But even then, there will be ambiguity. Planets are complicated. Atmospheres can fool us. Chemistry can produce surprises. Clouds can hide surfaces. A signal might be promising and still not definitive. The universe, as mentioned, enjoys keeping its options open. A real image would add a different kind of knowledge. Suppose we could see an exoplanet with enough detail to watch its rotation. We might see white clouds forming and dissolving. We might see dark and light regions returning every day. We might see polar caps growing and shrinking with seasons. We might see blue areas that suggest oceans or reddish deserts or global haze. We might compare weather patterns over time. We might learn whether the planet has stable surface conditions or wild changes. We might see whether its atmosphere circulates heat from day to night, if it is tidally locked, with one side always facing its star. We might start to understand the planet as a dynamic world rather than a set of numbers. The difficulty is that making such an image with a normal telescope would require a collecting system of breathtaking size. The detail a telescope can see depends on the wavelength of light and the diameter of the telescope. Larger telescopes can resolve finer details. This is why astronomers build bigger mirrors and link telescopes together as interferometers. But an Earth-sized planet at interstellar distance is such a tiny target that resolving its surface would demand an instrument far beyond ordinary construction. Even if we built a mirror in space much larger than anything today, we would still struggle to get the kind of image people dream about. The planet's angular size is just too small. It helps to picture the scale. Earth is about 12,742 kilometers across. That is large to us. It contains every ocean, every country, every forest, every city, every person who has ever misplaced their keys and blamed the sofa. But from several light years away, Earth would subtend an angle so tiny that ordinary language starts to fail. A telescope near Earth looking at another Earth around another star is not like looking at a marble across a room. It is more like trying to read the date on a coin on another continent while standing beside a floodlight. Actually, that may still be too generous. This is why the next generation of exoplanet observatories, as powerful as they may be, will still face limits. They may image more planets. They may study atmospheres. They may detect biosignature gases if nature is kind and the instruments perform well. They may give us the first strong evidence of life beyond Earth. But detailed surface imaging is another level. It is not just the next step on the same staircase. It is more like discovering the staircase continues up the side of a mountain and someone has removed several railings. There's also the issue of contrast. Even if a telescope has enough resolution, it must suppress the star's light enough to see the planet. This is where coronagraphs and starshades come in. A coronagraph blocks the light of the star inside the telescope, creating an artificial eclipse. A starshade would be a separate spacecraft, shaped almost like a giant flower, flying far in front of a telescope to block starlight before it enters the instrument. These technologies are beautiful examples of practical imagination. They are designed not to make the planet brighter, but to make the star less overwhelming. Sometimes seeing is not about adding light, it is about carefully removing the light that gets in the way. But even with such techniques, the planet remains small. You may detect it, you may study its spectrum, you may even measure changes as it rotates. Yet the dream of seeing its surface in detail remains beyond the reach of any telescope we can simply launch near Earth. That is the gap the solar gravitational lens might fill. It does not merely improve the telescope, it changes the rules of the telescope. Instead of building a mirror the size of a planet, we use the curvature of space-time around the sun. Instead of collecting light with glass alone, we let gravity bend and concentrate light for us. It is the sort of solution that feels less like inventing a new tool and more like noticing that the universe has been offering one quietly all along. Before we reach that solution, though, it is worth staying with the frustration a little longer, because it is a very human frustration. We've become good at discovering worlds we cannot see. There is something almost dreamlike about that. Astronomers can say, with confidence, that a planet exists around a star whose light has travelled for years or centuries to reach us. They can estimate its radius, its mass, its year, maybe its temperature. They may know that it is likely rocky or gaseous, close to its star or far away, inflated, scorched, frozen, or drifting through a strange orbit. But when the public asks, quite reasonably, what does it look like? The honest answer is often, we do not know. We might have an artist's impression, we might have a simulated view, we might have a curve on a graph, but not the view itself. Artists' impressions are useful and often beautiful, but they are not evidence in the same way an image is evidence. They are educated imagination. They help us feel what the data suggests. They turn mass, radius, and temperature into a visual story. But if a planet is shown with oceans, that does not mean oceans have been seen. If clouds are painted above its surface, that may be based on atmospheric clues, or it may be an artistic choice. If a red dwarf glows huge in the sky, the size may be chosen for drama or accuracy depending on the context. These images are bridges between data and human understanding, and they matter. But they can also make distant worlds feel more known than they really are. The real scientific picture is more modest and more impressive at the same time. We're standing on one planet, around one star, using fragile instruments to detect other planets, across distances so large that even light takes years to cross them. The fact that we can know anything at all about those worlds is astonishing. A dip in brightness smaller than 1%. A wobble measured in meters per second. A spectrum where a tiny missing band hints at a molecule. This is not failure. This is a civilization learning to read the universe by candlelight from the far side of a valley. Still, there is a difference between knowing that a planet exists and seeing it. There is a difference between detecting an atmosphere and watching clouds move. There is a difference between estimating that a world might be habitable and seeing the blue-white pattern of a living planet turn slowly against black space. That difference is why the idea of the sun as a telescope feels so powerful. It answers a longing that has been building since the first exoplanets were discovered. We do not only want to count worlds, we want to meet them with our eyes. Imagine for a moment how future astronomers might look back on this era. They may see us as living in the age of first detection, the age of shadows and wobbles, the age when humanity learned that planets were everywhere but could hardly see them. They may admire the ingenuity and also smile at the limitations, the way we smile now at early maps with sea monsters in the margins. Not because those map makers were foolish, but because they were working at the edge of what was possible. Our current exoplanet catalogue may be like that, a growing map of worlds full of numbers and names but still waiting for detail, and the names themselves carry a kind of distance. Kepler 452b, TRAPPIST-1e, Proxima Centauri b, LHS114OB, TOI this, K2 that, HD something else. Catalogue names are practical, but they do not feel like places yet. They feel like labels on sealed envelopes. Inside one of those envelopes may be a dead rock. Inside another may be a planet with air and weather. Inside another may be a world that has been changing for billions of years under a red sun. We do not know. The envelope is too far away, and the writing is very small. That is why the phrase blurry dots matters. It is not an insult to our telescopes. It is a description of the frontier. Blurry dots are where many great sciences begin. The first asteroids were dots. The first galaxies were fuzzy patches. Pluto was a tiny moving point. The moons of the outer planets were once little specks near brighter worlds. Over time, better instruments turned dots into disks, disks into landscapes, landscapes into geology, weather, chemistry, and history. Mars was once a reddish wandering light. Now we have rovers driving across it. Jupiter was once a bright point. Now we watch storms bigger than Earth roll through its clouds. Titan was once a dot near Saturn. Now we know it has lakes of methane and an atmosphere thicker than Earth's. The story of astronomy is often the story of dots becoming worlds. Exoplanets are still near the beginning of that transformation. We have learned that they are common, varied, and often surprising. We have found hot Jupiters that race around their stars in days. We have found super-Earths and mini-Neptunes, types of planets not represented in our own solar system. We have found compact systems where several worlds orbit closer than Mercury does to the Sun. We have found planets around red dwarfs, planets around binary stars, planets in strange orbits, planets being evaporated, and planets so hot that metals may vaporize in their atmospheres. The universe has not been boring in its planet making. It has been almost unnecessarily creative, like someone asked for a simple dinner and received a 12-course meal served in zero gravity. But the more variety we find, the more we want to see. Are rocky planets around red dwarfs stripped and barren? Or can some keep atmospheres? Do ocean worlds look blue from far away, or are they hidden under clouds and ice? Do tidally locked planets have permanent day sides and night sides with rings of habitability near the twilight zone? Do Earth-like planets actually look like Earth, or would we barely recognize them? Could life alter the colors of a planet in ways we might see? Would alien vegetation, if it exists, reflect light like plants here, or would it use different pigments under different stars? These questions are not answered by a dot alone. A blurry dot can become brighter or dimmer. It can redden or blue. It can reveal gases. It can suggest rotation. It can tease us with hints. But it cannot show us the shape of a continent, the edge of an ice cap, the movement of a storm system, or the glow of a night side. For that, we need a telescope with power beyond anything we can build in the usual way. We need an observing method that does not ask us to manufacture a mirror the size of a world. We need to borrow scale from nature, and nature has already built something large enough. It is outside every day, whether hidden by clouds or shining through the window. It is not polished. It has no tripod. It does not come with a user manual, which is probably for the best because the manual would begin with travel at least 550 astronomical units away and align yourself with a target several light years distant, and most people would put it back in the box, but the principle is there. The sun bends light. Its gravity curves the path of photons passing near it. From the right place far beyond the planets, that bending can be used. The same star that blinds our telescopes when we look too close to it may help us see planets around other stars with a level of detail that normal telescopes cannot reach. Long before we imagined using the sun as a telescope, we first had to learn something deeply strange about light. Light seems, at first, like the straightest thing in the universe. It shoots through a window in a clean line, It casts shadows with sharp edges. It travels from a lamp to a wall, from a star to your eye, from the morning sun to a half-awake person wondering where they left their tea. In everyday life, light behaves as if it knows exactly where it is going. It does not wander around corners unless reflected. It does not politely curve around furniture. It does not bend toward a sandwich because the sandwich looks interesting. It moves in straight paths, or at least that is how it seems to us in the small, gentle scale of kitchens, bedrooms, streets, and ordinary lamps. But the universe, as usual, is more flexible than it first appears. Light travels in straight lines only when the space it travels through is itself straight. And that is the trick. Space is not always straight. Space can curve. Time can curve with it. The fabric through which light moves can be shaped by mass and energy. So when light passes near something massive, such as a star, a galaxy, or a cluster of galaxies, the light still follows the straightest possible path available to it, but that path has been bent by the shape of space-time itself. From our point of view, it looks as though gravity has pulled on the light. More carefully, Einstein would say that gravity has changed the geometry, and light is simply obeying the new shape of the road. That idea did not come easily to human thinking. For centuries, gravity was understood through the work of Isaac Newton, who described it as an attractive force between masses. Newton's gravity was enormously successful. It explained falling apples, orbiting moons, planetary motion, tides, cannonballs, and many other things that move in ways people either admire or try to avoid. In Newton's picture, gravity pulled on objects with mass. A planet pulled on a moon. Earth pulled on a falling stone. The sun pulled on Earth. It was clean, powerful, and mathematically beautiful. But light was a little awkward in this picture. Light has no ordinary rest mass. So could gravity affect it? Some thinkers suspected it might, especially if light behaved partly like a stream of particles, but the deeper explanation had to wait for Einstein. Einstein did not begin by trying to design the ultimate telescope. He was trying to understand something much more basic. What is gravity, really? Why does it act the same on everything? Why do all objects fall at the same rate in a gravitational field if air resistance is removed? A feather and hammer dropped on the moon fall together, not because they are the same kind of object, but because gravity seems to affect motion in a universal way. Einstein took this very seriously. He imagined elevators in space. He imagined people falling. He imagined what it would be like if gravity and acceleration were somehow two sides of the same coin. This was not casual daydreaming, though one suspects Einstein would have been excellent at staring out of windows with great purpose. One of his key insights was the equivalence principle. In simple terms, it says that being in a gravitational field and being in an accelerating frame can feel the same locally. If you were inside a closed elevator with no windows, you might not be able to tell whether you were standing on Earth under gravity or being accelerated upward through space by a rocket. Your feet would press against the floor either way. Your dropped biscuit would fall to the floor either way, which is unfortunate but scientifically useful. From that starting point, Einstein developed general relativity, a theory in which gravity was not a force in the old Newtonian sense, but a result of curved space-time. Space-time is the combined fabric of space and time. That may sound grand, but the basic picture is manageable. Events do not happen only somewhere, they also happen somewhen. A sneeze, a sunrise, a comet passing behind Jupiter, the unfortunate moment when a cat knocks over a glass of water, each has a place and a time. Einstein's theory treats space and time as part of one connected structure. Mass and energy tell that structure how to curve. The curved structure tells matter and light how to move. This is often summarized as matter tells space-time how to curve, and space-time tells matter how to move. It is a tidy phrase for an idea that took enormous work to develop, and still makes the brain pause for a moment, like it has stepped onto a moving walkway without noticing. The usual analogy is a stretched rubber sheet. Place a heavy ball on it, and the sheet dips, roll a smaller ball nearby and it curves around the dip. This can help, but it is also imperfect because the rubber sheet is two-dimensional and needs gravity to pull the heavy ball downward in the first place. Real space-time curvature is not a sagging blanket in a room. It is the geometry of space and time changing around mass. Still, the analogy gives a gentle start. A star like the Sun curves space-time around it. Planets follow paths through that curved space-time, and those paths look to us like orbits. Light also follows paths through curved space-time, so light passing near the Sun does not travel exactly as it would in empty, flat space. Its direction changes. This was one of the great tests of general relativity. Einstein predicted that starlight passing near the Sun should be deflected by a small but measurable amount. The problem, of course, is that you cannot normally see stars right next to the Sun because the Sun is inconsiderately bright. Daylight washes them out. The solution was to wait for a total solar eclipse, when the Moon blocks the bright face of the Sun and allows nearby stars to be seen. In 1919, expeditions led by Arthur Eddington and others observed an eclipse and measured the apparent positions of stars near the Sun. Those stars seemed shifted from where they would normally be, just as Einstein's theory predicted. The light from the stars had bent as it passed through the curved space-time near the Sun. That moment became famous, partly because it confirmed a daring theory, and partly because newspapers enjoy sentences like "Newton overthrown" when they can get them. Newton was not exactly thrown into a ditch, of course. His physics still works beautifully for everyday speeds, weak gravity, and most practical purposes. If you drop a spoon, you do not need general relativity to predict the sadness of the floor. But Einstein revealed a deeper layer. Gravity was not merely a pull, it was geometry. And light, even though it has no rest mass, could be guided by that geometry. The effect near the Sun is small for a single ray of light. A star's apparent position shifts by a tiny angle when its light passes close to the solar limb. But small does not mean unimportant. The whole history of precision astronomy is built from tiny effects measured carefully. A slight wobble reveals a planet. A faint dimming reveals a transit. A small shift in starlight reveals curved space-time. Nature often whispers the biggest truths in very small numbers, perhaps because it knows astronomers are willing to listen for a long time. Once scientists understood that gravity bends light, a new kind of cosmic tool became possible. Massive objects could act as lenses, not glass lenses, not lenses you could hold, polish, or accidentally smudge with a fingerprint. Gravitational lenses. When light from a distant object passes near a massive object between us and it, the foreground object bends the light, changing the image of the background object. Sometimes the background object appears brighter. Sometimes it appears stretched into arcs. Sometimes it appears multiple times in different places. In special alignments, it can form a ring around the lensing object, called an Einstein ring. These rings are not solid structures. They are images, made by light from something behind the lens being bent around it and directed toward us. This is one of the most useful gifts of general relativity. Across the universe, astronomers use gravitational lensing to study things they could not otherwise see. A massive galaxy cluster can magnify galaxies far behind it, making them visible even though their light has travelled across much of cosmic history. Lensing can reveal the presence of dark matter, because the amount of bending depends on the total mass, including mass we cannot see directly. Lensing can even help find exoplanets through microlensing, when a star and its planet briefly magnify the light of a more distant background star. Gravity becomes a kind of cosmic magnifying glass, though one with no handle and very strict alignment requirements. There are several kinds of gravitational lensing. Strong lensing produces dramatic arcs, multiple images, and rings when the alignment is good and the lens is massive enough. Weak lensing is subtler, slightly distorting the shapes of many background galaxies, and astronomers use statistical methods to map mass across vast regions. Microlensing produces temporary brightening events when smaller objects like stars or planets pass in front of background stars. The underlying principle is the same in all cases. Mass curves space-time. Light follows that curvature. What changes is the scale, the alignment, and the kind of information we can extract. The important point for our story is that the Sun is massive enough to bend light in a useful way. It is not as massive as a galaxy cluster, of course, and it cannot produce the giant arcs we see in deep cosmic images. But it is close to us. Very close, by astronomical standards. We can travel around it. We can position spacecraft relative to it. We can use it deliberately, at least in principle. That is what makes the solar gravitational lens so intriguing. Many gravitational lenses in the universe are found by chance. They depend on massive objects happening to sit between us and something more distant. But with the Sun, the lens is our own star. We know where it is. We know its mass. We understand its gravitational field very well. We cannot move it, thankfully, but we can move ourselves. The Sun bends light from every distant object whose rays pass near it. If you are in the right place on the far side of the Sun, the bent light from a distant target can be concentrated along a line. For the Sun, that useful focal region begins around 550 astronomical units away. It is often described as a focal line rather than a focal point because the Sun is not a simple glass lens. Light passing at different distances from the Sun focuses at different distances beyond it. Rays skimming close to the Sun start focusing at about 550 astronomical units, while rays passing farther out focus farther away. This means a spacecraft does not need to hit one tiny point in space, which is merciful, because navigating to one exact point, hundreds of astronomical units away, would be a little much even for a species that keeps losing TV remotes. Instead, it must travel along the correct direction beyond the Sun, aligned with the target star and planet. From there, the distant planet's light would appear around the Sun as an Einstein ring. Imagine the Sun in front of you, blocked by a coronagraph so its glare is reduced. Around it, very close to the solar edge from your viewpoint, is a thin ring or partial ring of light. Hidden in that ring is the light from the exoplanet, bent and amplified by the Sun's gravity. The image is not simple. The planet is not neatly projected like a slide on a screen. The light from different parts of the planet becomes mixed around the ring. There is also light from the planet's host star, light from the solar corona, instrument noise, and all the practical messiness that comes with real observations, but mathematics can help untangle it. By moving the spacecraft across the projected image and measuring changes, scientists could reconstruct a picture of the planet. This is where Einstein's strange gift becomes practical. The same theory that tells us clocks tick differently in different gravitational fields also tells us how light curves around the Sun. The same bending that once shifted star positions during an eclipse could, with enough engineering and patience, become a tool for seeing continents on another world. It is a remarkable transformation. A tiny measured deflection in 1919 becomes, in the future, a possible route to imaging an exoplanet in detail. Science often works this way. An idea begins as a test of a theory, then becomes a tool, then becomes a door into something nobody could have done before. It is worth slowing down on the phrase, "gravity bends light," because it can be misunderstood. Gravity is not grabbing a photon with a tiny invisible hand. Photons travel at the speed of light, and from their point of view, if photons can be said to have a point of view, the journey is not like a little bead being tugged sideways. In general relativity, objects moving freely follow paths called geodesics, the straightest possible paths through curved space-time. On the surface of Earth, the shortest path between two distant points is not a straight line on a flat map, but a great circle route on a sphere. Airplanes often follow these curved-looking paths because the surface itself is curved. In a similar way, light near a massive object follows the straightest available path in curved space-time. To us, mapping the path against a flat expectation, it appears bent. This distinction matters because it shows how profound the idea really is. Einstein did not merely add one more force to the universe, he changed the stage on which motion happens. Under Newton, space and time were like a fixed arena where objects moved and forces acted. Under Einstein, the arena itself responds. It curves, it stretches, it changes depending on mass and energy. Light does not ignore that arena, it reveals it. In fact, light is one of our best messengers of space-time's shape. When light arrives distorted, delayed, magnified, or split into multiple images, it carries news of the gravitational landscape it crossed. Gravitational lensing can also magnify without behaving exactly like a household magnifying glass. A glass lens bends light because light changes speed when it enters and exits the material. The shape of the glass redirects rays toward a focus. A gravitational lens bends light because space-time is curved by mass. There is no material lens. Nothing touches the light. The focusing is created by geometry. This is why a star can act as a lens without being transparent in the ordinary sense. Light does not pass through the sun. That would not end well for the light or for any spacecraft waiting politely behind it. The light passes around the sun, through the curved space-time near it. The sun's mass redirects the paths of those rays. There is a small complication here that will matter later. The sun is not alone in the sky. It shines. It has a corona, a hot outer atmosphere that extends far into space. Any spacecraft trying to use the sun as a lens must deal with the sun's own brightness and the light from that corona. It must block the central solar disk and separate the faint Einstein ring from the surrounding glow. This is difficult, but not a reason to abandon the idea. Astronomy is full of difficult light problems. We have learned to block stars, subtract backgrounds, calibrate detectors, and extract faint signals from noise. The solar gravitational lens would push these techniques very far, but it does not ask them to break physics. It asks them to be extremely good. The gift also comes with a very long address. To use the sun's lens, we must travel hundreds of astronomical units away. Earth is 1 astronomical unit from the sun. Jupiter is about 5 astronomical units. Saturn is about 9.5 astronomical units. Neptune is about 30 astronomical units. Pluto's orbit takes it roughly between 30 and 49 astronomical units from the sun. The beginning of the solar gravitational focal region, around 550 astronomical units, is far beyond all of that. It is a distance that makes the solar system feel less like a tidy diagram, and more like an enormous dark field with the known planets clustered near the centre. Our usual maps are misleading because they compress emptiness to fit on a page. If Earth's orbit were a small circle on a desk, 550 astronomical units would put the focal line somewhere embarrassingly far out in the hallway, possibly through a wall, depending on the scale and the patience of the person explaining it. But distance is also part of why the idea is powerful. By going far away, a spacecraft can place itself where the sun's gravity has brought the light into a usable alignment. It is not enough to build a powerful camera near Earth. The geometry does not work here. We have to go to where the lens focuses. That means the telescope is not located in one object. It is a system. The distant exoplanet, the sun as the lens, the spacecraft far beyond the sun, and the line connecting them. The telescope is made of distance as much as mass. It is made of alignment, patience, and the shape of space-time. There is something humbling about that. Human engineering often feels like an act of control. We build mirrors, detectors, rockets, antennas. We shape metal and glass. We write software. We test, launch, correct, and operate. But the solar gravitational lens asks for a different kind of partnership. We cannot redesign the sun. We cannot polish its gravitational field. We cannot move the focal line closer because we would prefer a shorter commute. We have to accept the geometry nature provides and send our machines to meet it. it is less like building a telescope from scratch and more like discovering that a mountain casts a perfect echo if you stand in one exact valley. Einstein probably did not imagine that his equations would someday inspire proposals to image alien continents. He was dealing with the foundations of reality, not planning sightseeing tours of Proxima Centauri b. Yet this is one of the quiet pleasures of science. A theory developed to explain one mystery becomes useful in places its creator did not foresee. General relativity gave us gravitational lensing, black holes, gravitational waves, corrections for GPS satellites, and now perhaps a path toward imaging worlds around other stars. It is a reminder that understanding is not only satisfying in itself, it can become an instrument. As we move deeper into this idea, the sun begins to look different. Not visually, perhaps. It is still the bright disk that warms the day and hides the stars. It is still the centre of our weather and the anchor of our planets. But conceptually, it changes. It is no longer only the object our telescopes must avoid when searching the daytime sky. It becomes part of the observing apparatus. The gravity that keeps Earth in orbit could also gather light from a planet many light years away. This star that outshines everything near it could help reveal something too faint for our ordinary mirrors. The familiar sun becomes a lens so enormous that the word telescope begins to feel too small. Once you understand that gravity can bend light, the sun begins to feel different. It is still the same star, of course. It still rises and sets from our point of view. It still warms the ground, lights the clouds, powers the weather, and gives houseplants something to lean toward with quiet determination. But now, behind all that familiar brightness, another possibility appears. The sun is not only a source of light, it is also a massive object sitting in space, and because it is massive, it curves the space-time around it. Light from distant objects passing near the sun does not travel past untouched. It is bent, redirected, and very slightly gathered by the sun's gravity. That means the sun can act like a lens. Not a lens made of glass, not a lens that could be polished or cleaned with a little cloth, and certainly not one you would want to hold up to your eye. It is a gravitational lens made from mass and distance, and it may be the largest natural optical tool within our reach. That phrase, within our reach, needs to be handled carefully. The sun is close compared with other stars, but the place where its lens becomes useful is not close in the everyday sense. You cannot put a telescope in Earth orbit and use the full solar gravitational lens the way you might attach a camera to a tripod. The geometry is much more demanding. The light from a distant planet has to pass near the sun, curve around it, and then continue outward until those bent paths can be measured along the focal line far beyond the planets. For the sun, that useful region begins at roughly 550 astronomical units from the sun. Earth is 1 astronomical unit from the sun. Neptune is around 30. Pluto, depending on where it is in its orbit, stays within roughly a few dozen. So 550 astronomical units is not just a little past the edge of the familiar solar system. It is deep into the outer dark, where the sun has become a brilliant star behind you, rather than a broad daylight disk above you. Still, distance is part of what makes the idea work. A normal telescope gathers light with a mirror or lens. The larger the mirror, the more light it collects, and the finer the detail it can resolve. This is why astronomers build bigger and bigger telescopes. A larger opening can distinguish smaller angles on the sky, but there is only so large a mirror can realistically become before engineering starts looking at the proposal, clearing its throat, and asking whether everyone has had enough sleep. You can build a mirror several meters wide. You can build segmented mirrors that unfold in space. You can imagine future observatories with even larger structures. But if you want to image surface detail on an Earth-sized planet many light years away, the required resolving power becomes enormous. At some point, the telescope you would need is not simply difficult, it becomes physically unrealistic for any normal construction method. The sun changes the scale of the problem. Instead of building a single artificial mirror large enough to see another Earth clearly, we use the sun's gravitational field to bend and amplify the planet's light. The sun becomes the main optical element. The spacecraft becomes more like the detector placed far away at the right location. In that sense, the telescope is not just the spacecraft. It is the whole arrangement: the distant exoplanet, the sun, the curved space-time around the sun, and a small machine waiting far beyond the outer planets. It is a telescope stretched across the solar system. That is not how we usually picture an observatory. There is no dome, no mountain, no engineer walking through a clean room with a clipboard and a worried expression. But the principle is still optical. Light is being focused, information is being gathered, and an image can be reconstructed. A glass lens focuses light because the material changes the direction of incoming rays. The sun focuses light because its gravity changes the geometry those rays move through. The light does not pass through the sun. That would not be a telescope. That would be a very brief and unsuccessful experiment in sending photons through hot plasma. The useful light passes around the sun, especially near its edge from the observer's point of view. Rays passing on different sides of the sun are bent inward. If an observer is placed far enough away on the opposite side, those rays form a concentrated pattern. For a distant point source, the result can be a bright ring around the sun, an Einstein ring. For an extended object like a planet, the situation is more complicated, because the light from many different parts of the planet is bent and mixed together. But hidden in that ring is information about the world that emitted or reflected the light. This is what makes the sun a very unusual lens. It does not produce a neat little image in the way a camera lens does. If you take a photograph with a normal camera, the lens forms a familiar two-dimensional image on a sensor. A tree appears as a tree. A chair appears as a chair. A cat appears as a slightly judgmental cloud with legs, depending on the cat. The solar gravitational lens does not give us that kind of instant picture. The light is wrapped around the sun and compressed into a ring-shaped signal. The planet's image is spread out and blurred by the lensing process. To recover the planet, a spacecraft would have to measure the Einstein ring carefully, move through the image plane, sample many positions, and let computers reconstruct the original scene through mathematical inversion. This is not simple photography. It is more like decoding a message that has been folded, stretched, and posted around the edge of a star. Yet this difficult signal could contain extraordinary detail. The sun's gravitational lens has a theoretical resolving power, far beyond any telescope we can build in the ordinary way. Mission studies have described the possibility of imaging an exoplanet with many pixels, perhaps enough to show large-scale surface features. That would not necessarily mean a crisp holiday postcard from another solar system. We should keep our expectations disciplined. The image would be reconstructed, noisy, and shaped by real observational limits. Clouds move, planets rotate, atmospheres scatter light. The sun's corona adds background brightness. Instruments have errors, data processing has assumptions, but even with those warnings, the leap from a dot to a resolved world would be enormous. It would be the difference between knowing a house exists somewhere in a foggy valley and beginning to see its roof, its fields, and the road that leads toward it. The sun's advantage comes from gravity doing what no solid mirror could do at that scale. If we tried to build a conventional telescope with comparable resolving power, the structure would have to be absurdly large. It would make our greatest observatories look like small household items. Even space telescopes that seem grand to us are tiny, compared with the effective scale of a gravitational lens. The sun's lensing effect is not limited by a physical edge in the same way a mirror is. Its gravitational field extends outward, and light passing near it can be focused along a long line. In one sense, the sun is not a telescope with a diameter you can measure by walking from one side of a mirror to the other. It is a lensing system, with a huge natural aperture set by the paths of light around the Sun's mass. The useful instrument includes a star-sized gravitational field. This does not make the Sun magically perfect. Nature gives us scale, but not convenience. A normal telescope can be pointed from one target to another. A space telescope can change its orientation and observe many objects across the sky. The solar gravitational lens is much more stubborn. To observe a particular exoplanet, the spacecraft must be located on the line opposite that target, with the Sun between the spacecraft and the planet. If you want to observe a different target in a very different direction, you cannot simply turn the telescope. You may need a different spacecraft on a different line, or a long and difficult repositioning. The Sun as a lens is incredibly powerful, but it is not flexible in the way an observatory near Earth is flexible. It is more like a gigantic natural instrument that only works when you stand in the correct place and face the correct direction. This makes target selection important. A mission using the solar gravitational lens would likely focus on one carefully chosen planet, or perhaps a small set of targets if the mission design allowed. The planet would need to be scientifically valuable enough to justify the enormous journey. Nearby rocky planets would be especially interesting, because closer targets are easier to image in detail than more distant ones. A world in the habitable zone of a nearby star would attract attention. A planet with prior hints of an atmosphere, liquid water conditions, or unusual chemistry might become a candidate. By the time such a mission becomes possible, our exoplanet catalogues will likely be far better than they are today. Future observatories may already have identified promising worlds and studied their atmospheres enough to say, "That one, go look at that one properly." In this way, the solar gravitational lens would not replace other telescopes. It would depend on them. Before we send a spacecraft hundreds of astronomical units away, we need to know where to send it. We need target stars, orbital data, planetary sizes, atmospheric clues, and a good understanding of how the planet moves. Telescopes near Earth, in Earth orbit, on the Moon perhaps, or farther out in space would act as scouts. They would find the candidates and narrow the list. The Sun's lens would be the follow-up tool for a world so interesting that humanity is willing to send a machine to the far edge of our practical reach just to see it. There is a nice humility in that. The greatest telescope ever built may not be a single machine at all. It may be a chain of instruments and ideas. First, smaller telescopes detect the planet. Then more advanced observatories study its atmosphere. Then mission planners choose the target. Then solar sail spacecraft or other fast probes travel outward. Then one of them reaches the focal region and begins sampling the Einstein ring. Then computers on Earth, or perhaps on board the probe, reconstruct an image from the data. The final picture would be the product of many tools working together: ordinary optics, gravitational optics, propulsion, navigation, communication, computation, and patience. Especially patience. Space exploration uses patience the way sailing uses wind. The sheer brightness of the Sun is one of the major practical problems. To use the Sun as a lens, the spacecraft must look back toward the Sun, because the lensed light appears around it. But the Sun is bright, and its outer atmosphere, the corona, glows around the solar disk. The Einstein ring from the exoplanet would be faint compared with the solar environment. So the spacecraft would need a coronagraph, an instrument that blocks the bright central disk of the Sun, creating an artificial eclipse inside the telescope. It would need to suppress glare, measure faint signals, and distinguish the planet's lensed light from background noise. That is a serious challenge. It's a little like trying to hear a whisper from across a field while standing next to a waterfall, except the waterfall is made of sunlight and plasma, and the whisper has travelled from another star. The Sun's corona is not just bright, it is structured and variable. It changes with solar activity. It contains streamers, magnetic features, and plasma that can affect observations. A real mission would need careful calibration and perhaps long observing times. It would need to understand the sun not only as a lens, but also as a source of noise. This is a slightly funny situation. The sun would be both the thing helping us see and the thing getting in the way. It is like borrowing someone's enormous magnifying glass while they keep waving a flashlight in your face. Still, astronomy has always involved separating signal from noise. The night sky is not a clean laboratory. Telescopes must deal with atmosphere, dust, cosmic rays, detector effects, scattered light, and every kind of inconvenient glow. The solar gravitational lens simply gives us a more ambitious version of the same old problem. Another complication is that the sun is not an ideal lens. It is not a perfect smooth point mass. It rotates. It is slightly flattened. It has planets around it, including Jupiter, whose gravity also affects the solar system. It has plasma around it. Its gravitational field is very well understood, but precision imaging would need extremely careful modelling. The spacecraft's position would need to be known accurately. The target planet's motion would need to be accounted for. If the exoplanet rotates during the observation, its clouds and surface features change. If it has weather, the image changes. If it orbits its star, illumination changes. The reconstruction process would need to account for a moving, changing world. That sounds frustrating, but it is also part of the appeal. A changing planet is a living physical system, not a painted ball. Weather, rotation, and seasons are the very things we want to learn about. The sun's lens also has a narrow field of view in a practical sense. Each position in the image plane corresponds to information about the target in a particular way. To build up an image, the spacecraft may need to move across a region of space, sampling different points. That means propulsion and guidance do not end when the probe arrives at 550 astronomical units or beyond. Arrival is not the finish line. It is the beginning of delicate work. The spacecraft must continue to maneuver, scan, measure, and communicate. It must do this far from the sun, where solar power is weak, where repairs are impossible, and where each radio message takes days to cross the distance back to Earth. A mission like this would be less like a quick visit, and more like establishing a tiny observatory in a remote wilderness. A very remote wilderness with no air, no warmth, and no nearby shops selling replacement parts. The reward would be a new kind of astronomy. We would not only be observing planets as dots or spectra, but as extended worlds. Suppose the target were an Earth-like planet around a nearby star. A reconstructed image might reveal whether the planet has large oceans or mostly land. It might show polar regions. It might show cloud belts or seasonal cloud patterns. It might show surface contrast that changes as the planet rotates. Over repeated observations, scientists could build up a sense of climate. They could compare visible light and infrared data. They could look for signs that the atmosphere and surface interact in stable ways. If the planet had life that strongly affected its atmosphere or reflectivity, the lens might help connect chemical clues with visible geography. This is where the sun's role becomes emotionally powerful, not just technically impressive. The same star that made life possible on Earth might help us study life elsewhere. The sun lit the first human eyes that looked upward. It powered the biosphere that eventually produced telescopes, mathematics, spacecraft, and people who stay up too late thinking about planets. In the future, the sun may help us see whether other biospheres exist around other stars. That is not poetry, so much as a straightforward chain of dependence. Our star made us possible, and its gravity may become one of the tools we use to understand whether we are part of a larger living universe. But there is no need to leap straight to life. Even a lifeless planet would be fascinating if seen in detail. A barren, rocky world could teach us how planets lose atmospheres. A frozen planet could show patterns of ice and geology. A cloudy mini-Earth could help us understand climate under different suns. A tidally locked world around a red dwarf could reveal heat transport between permanent day and permanent night. A planet with no life can still have a history. and a detailed image would be a kind of geological introduction. We have learned this lesson in our own solar system. Mars is not Earth, but it's not boring. Venus is hellish, but it is scientifically rich. Europa is an icy moon, yet it may hide an ocean. Titan has methane lakes under orange haze. Worlds do not need forests to be worth seeing. A solar gravitational lens mission would also force us to think about telescopes differently. We usually imagine progress as building bigger instruments close to home, bigger mirrors, better detectors, smarter software. Higher orbits, colder instruments, longer baselines, all of that will continue. But the sun's lens adds another category, going to the place where nature has already done part of the optical work. That is a different strategy. It says that the instrument is not always brought to the observer. Sometimes the observer must travel to the instrument. The telescope is out there already, written into the curvature around the sun, and our spacecraft has to go meet it. There are other gravitational lenses in the universe, some far more powerful in certain ways. Galaxy clusters can magnify distant galaxies. Black holes bend light dramatically. Massive galaxies create arcs and rings. But those lenses are far away and not under our control. The sun is local. Local again in the astronomical sense, not in the sense that you could pop over after lunch. Its gravitational field is stable, predictable, and accessible compared with other stars. Every star could, in principle, act as a gravitational lens, and an advanced civilization around another star might use its own sun in a similar way. The idea is not special because our sun is unique in being able to bend light. It is special because it is ours. It is the lens we can realistically hope to reach. This raises a quiet but interesting thought. If gravitational lenses are natural tools, then advanced civilizations might use them. If they wanted to image distant planets, communicate across interstellar distances, or study faint objects, stellar gravitational lenses would be attractive. A network of probes placed along focal lines around stars could serve as observatories or communication relays. This is speculative, but it follows from the same physics. Once a civilization understands gravity and can travel far enough from its star, it may discover that the outskirts of its planetary system are not empty wastelands, but useful locations. The deep dark beyond the planets becomes an observing platform. What looks like the edge of home becomes the beginning of a larger instrument. For humanity, that shift would be profound. Today, even reaching the outer planets is a major mission. The thought of sending purpose-built observatories hundreds of astronomical units away requires a different time horizon. It asks for faster propulsion, long-lived spacecraft, autonomous systems, and communication methods that can operate across enormous distances. It may involve swarms of small spacecraft rather than one large probe. It may involve solar sails, close passes by the sun, electric propulsion, nuclear power, or technologies still being developed. The sun as a lens is not just an astronomy concept. It is a challenge to our entire way of operating in space. To use it, we must become better at travelling through our own solar system. There's also a practical beauty in using what already exists. We do not need to manufacture the lens. We do not need to launch the sun. That would be difficult to schedule. The mass is already there. The curvature is already there. The focal line is already there. The missing piece is a spacecraft that can reach it and do useful work once it arrives. This is one reason the idea can feel both impossible and strangely sensible. We're not asking the universe to change its laws. We're asking whether our machines can become good enough to take advantage of laws we already know. From Earth, the sun can feel ordinary because it is always involved in ordinary things. Morning routines, weather forecasts, shadows on pavements, warm towels from the line, the slow fading of evening. But astronomy has a way of taking ordinary things and turning them around until their hidden scale becomes visible. The sun is an ordinary star in one sense, but ordinary stars are not small. Its mass curves space-time. Its light reaches every planet in the solar system. Its gravity holds together a family of worlds, moons, asteroids, comets, dust, and distant icy bodies. Now we add one more fact to that list. It can focus light from other stars' planets. It is difficult to keep the Sun mentally small after that. So when we say the Sun could become a natural lens bigger than any telescope, we do not mean it would look like a giant tube pointed at the sky. We mean that the Sun's gravity could provide an optical effect no built mirror can match. We mean that a modest spacecraft placed at an extraordinary distance could use the star's curved space-time to gather information from a planet that would otherwise remain a dot. We mean that the true instrument is not just hardware, but geometry. The telescope is made from an alignment between worlds. That alignment is strict. The target planet, the Sun, and the spacecraft must form a line. If the spacecraft drifts away from the right region, the signal changes. If the planet moves in its orbit, the geometry evolves. If the spacecraft wants to keep observing, it must track the target's motion by moving through space. This means the mission would require continuous precision, not just a heroic journey outward. It would be a long performance of navigation, a little probe far away, making tiny corrections, watching a ring of light around the Sun, and slowly turning that ring into a map. And now, the natural question becomes less about the lens itself and more about the road to it. If the useful region begins hundreds of astronomical units away, how do we get there in a reasonable time? Reaching the place where the Sun becomes useful as a telescope is not like sending a spacecraft to Mars, or even to Jupiter, or even to Pluto. Those journeys are already impressive enough. Mars takes months to reach. Jupiter takes years. Pluto required nearly a decade of flight by New Horizons, even with a fast launch and a helpful gravitational push from Jupiter. But the solar gravitational focal region is much farther out than Pluto, farther out than the familiar planets, farther out than the diagrams of the solar system most of us grew up seeing on classroom walls. It begins hundreds of times farther from the Sun than Earth is. Somewhere beyond about 550 astronomical units, the Sun's gravity has bent light from distant objects enough that a spacecraft can begin to use that focused light. That is where the telescope made of sunlight, gravity, distance, and patience truly begins to work. An astronomical unit sounds tidy because it has a neat name, but it is enormous. 1 astronomical unit is the average distance between Earth and the Sun, about 150 million kilometers. Light crosses that distance in a little over 8 minutes. When you feel sunlight on your face, you're feeling light that left the solar surface several minutes ago, which means daylight itself is always slightly old. Not old in a dramatic way, not old like a fossil or a forgotten sandwich at the back of the refrigerator, but old enough to remind us that even the Sun is not immediate. Now multiply that Earth-Sun distance by 550. That is the beginning of the region we're talking about. Light from Earth would take more than 3 days to travel there. A radio message from the spacecraft would take more than 3 days to come home, and then more than 3 days for a reply to reach it. A simple conversation with the probe would feel less like texting, and more like sending letters across an ocean in the age of sail. This distance is difficult to picture because our usual mental map of the solar system is badly compressed. We tend to imagine the planets spaced like beads on a necklace, with Neptune and Pluto somewhere near the outer edge, and then perhaps the stars beginning not too far beyond. But the real solar system is mostly distance. Earth orbits at 1 astronomical unit. Mars is around 1.5 astronomical units from the Sun. Jupiter is about 5 astronomical units. Saturn is around 9.5 astronomical units. Uranus is about 19 astronomical units. Neptune is about 30 astronomical units. Pluto wanders through a stretched orbit that keeps it roughly within a few dozen astronomical units. And then, after all that, you still have to keep going. Not a little, a lot. The solar gravitational focal region begins at more than 10 times Pluto's average distance from the Sun. It is the kind of distance that makes the outer planets feel less like the edge of the solar system and more like the front porch. Voyager 1 helps make the scale real. It was launched in 1977, flew past Jupiter and Saturn, and then continued outward, becoming one of humanity's farthest travelling spacecraft. After decades of flight, it has crossed into interstellar space in the sense of moving beyond the main bubble of the solar wind, but it is still nowhere near 550 astronomical units. Voyager is a miracle of engineering, a machine from another era still speaking faintly across the dark. But if we relied on Voyager-like speeds for a solar gravitational lens mission, the wait would be extremely long. Long enough that mission planners, scientists, and probably several generations of patient graduate students would have to pass the work along like a very delicate family recipe. So if we want to use the Sun as a telescope within something like a human lifetime, we need speed. Not science fiction speed, not warp drives, not hyperspace, not pressing a glowing blue button labelled faster than light, which is always suspicious in films. We need realistic speed, but much greater than the speed of our traditional deep space probes. Some mission studies imagine reaching the focal region in a few decades rather than a century. To do that, spacecraft must travel outward at many astronomical units per year. That is a demanding pace. It requires a mission architecture built around low mass, efficient propulsion, careful trajectory design, and technology that can keep working for a very long time. One of the most elegant ideas is to use solar sails. A solar sail is a large, thin, reflective surface that catches the pressure of sunlight. Light has no rest mass, but it carries momentum. When photons bounce off a sail, they give it a tiny push. The push is gentle, almost laughably gentle if you compare it to a rocket engine. You will not be thrown back into your seat. There is no thunder, no flame, no dramatic cloud of exhaust. But sunlight pushes continuously, and in space, where there is no air resistance, a continuous small push can build up speed over time. The trick is to make the spacecraft very light and the sail very large. The sail needs to catch as much sunlight as possible while carrying as little mass as possible. In other words, it wants to be a cosmic feather with excellent posture. Solar sailing becomes especially powerful close to the Sun, where sunlight is much more intense. One concept for reaching the solar gravitational lens involves sending small sailcraft inward toward the Sun first, rather than outward directly. That may sound backwards, like driving toward the city centre in order to reach the countryside, but orbital mechanics often has a sense of humour. By diving close to the Sun, a spacecraft can unfold or orient a sail where sunlight is strongest, gaining a powerful push outward. The sail then uses that burst of sunlight pressure to leave the inner solar system at high speed. In this picture, the Sun helps in two ways. It gives the spacecraft the shove it needs to travel far away, and later, once the spacecraft reaches the distant focal region, the Sun's gravity becomes the lens for imaging another planet. The same star provides the wind and the telescope. There are many practical problems hidden inside that sentence. A spacecraft that dives close to the Sun must survive heat, radiation, and intense sunlight. A sail must be thin enough to keep the spacecraft light, but strong enough to deploy, reflect, and maintain its shape. It must handle thermal stress. It must be aimed precisely. If the sail tears, wrinkles badly, or points the wrong way, the trajectory can change. There is something almost absurdly delicate about the idea. A very thin sheet of material, unfurled near the most powerful object in the solar system, used to fling a small probe into the outer dark. It sounds like launching a paper kite from beside a furnace and asking it to fly to another continent. Yet the physics is real, and solar sails have already been tested on smaller missions. The challenge is scaling the idea, hardening it, and making it reliable enough for a journey measured in decades. Another approach might involve other propulsion systems. Electric propulsion can be efficient, though it usually provides low thrust. Nuclear electric propulsion has been discussed for deep space missions because it could provide power far from the Sun and potentially push a spacecraft for long periods. Gravity assists might help in some trajectories, though they cannot solve the entire problem by themselves. Future mission planners may combine methods: launch energy from Earth, a close solar pass, sail acceleration, perhaps modular assembly, perhaps multiple small probes. The final architecture may not be one grand spacecraft, but a swarm or sequence of smaller ones, each designed to be affordable enough, fast enough, and resilient enough to make the journey. Small spacecraft make sense for another reason. A mission to the solar gravitational lens may benefit from sending several craft rather than one. The focal region is not one easy point, and imaging requires movement across the image plane. Multiple probes could sample different regions, provide redundancy, and reduce the risk that one failure ends the entire mission. A fleet of small sailcraft could be launched over time, each heading toward the line for a chosen target. Some might carry instruments, some might act as communication relays, some might help with navigation or calibration. This is not a settled design, but the idea fits the scale of the problem. When the destination is hundreds of astronomical units away, and the mission could last decades, it is comforting to avoid putting every hope into one lonely machine with no backup and no nearby repair shop. The journey outward would pass through familiar regions first, though at high speed they would not remain familiar for long. The spacecraft would leave Earth, pass through the inner solar system, perhaps swing close to the Sun, and then accelerate outward. It might cross the orbit of Mercury, Venus, Earth, Mars, and the asteroid belt. Jupiter's orbit would pass. Saturn, Uranus, and Neptune would fall behind. Each of those distances, which once defined the grand scale of planetary exploration, would become a milestone on a much longer road. The spacecraft might pass the orbit of Pluto in only a fraction of the time older probes required, depending on its final speed. Then it would enter the deep outer solar system, where sunlight fades and the planets are all behind it. As the spacecraft travels farther from the Sun, power becomes a serious question. Solar panels work beautifully near Earth and can still function at Mars and even beyond with the right design. But at hundreds of astronomical units, the Sun is just a bright star. The sunlight there is far too weak for ordinary solar power to be useful for a demanding observatory. A probe operating in the focal region would likely need nuclear power, perhaps radioisotope systems or other long-lived power sources. It must run instruments, computers, communications, heaters, and navigation systems. Space is cold, but electronics do not simply enjoy freezing politely for decades. The spacecraft needs thermal control. It needs to keep its systems alive. It needs to wake, measure, process, transmit, and adjust, all while farther from home than any practical servicing mission could reach. Communication is another difficulty. A spacecraft at 550 astronomical units is not just far away, it is faint to us. Its radio signal spreads out across space. By the time it reaches Earth, it's extraordinarily weak. Large antennas on Earth, perhaps the Deep Space Network or future arrays, would need to listen carefully. The spacecraft might need a high-gain antenna aimed with great precision back toward Earth. But aiming is not trivial when the probe is also trying to observe the Einstein ring around the Sun. It must manage power, pointing, data storage, and communication schedules. It may need autonomy because waiting a week for a command response cycle is too slow for many operations. The spacecraft cannot rely on Earth for every little adjustment. It must be able to look after itself in the quiet. Navigation becomes almost philosophical at this distance. Near Earth, we can track spacecraft with great precision, but the farther away they go, the harder everything becomes. A solar gravitational lens mission must not only reach a distant radius from the Sun, it must reach the correct line. The target exoplanet, its star, the Sun, and the spacecraft must be aligned. The spacecraft is not travelling to a place marked by a planet or moon. There is no object waiting there, no surface, no orbiting station, no signpost saying, "Welcome to the focal line, please enjoy the view." It is travelling to a geometric location defined by a distant star system and the Sun's gravitational field. The destination is a relationship. This makes the journey unusually abstract. A Mars mission goes to Mars. A Jupiter mission goes to Jupiter. A solar gravitational lens mission goes to a line in space where light from a planet around another star has been bent by the Sun into a measurable pattern. That is a harder thing to explain at dinner table. It is also a beautiful example of how advanced astronomy changes our sense of location. We begin to travel not only to worlds but to viewpoints. A place becomes important because of what can be seen from there. The focal region is not valuable because it contains a hidden treasure chest or a scenic overlook in the usual sense. It is valuable because from there, the Sun and a distant planet line up in such a way that information becomes available. By the time the spacecraft nears 550 astronomical units, the Sun would look very different from how it looks from Earth. It would still be the brightest star in the sky, but no longer a broad disk blazing overhead. It would be small and intense, far behind the spacecraft. The planets would be invisible or nearly so without instruments. Earth would be lost close to the Sun's glare. Home would be a direction and a signal, not a visible blue marble. The probe would be alone in a region so quiet that the word quiet almost stops working. There would be no wind, no sound, no familiar horizon. Just distant stars, cosmic rays, faint dust, the thin remains of the Sun's influence, and the spacecraft's own systems humming in silence. And yet the spacecraft would not have gone there for emptiness. It would have gone there because emptiness, properly positioned, can become an observatory. Once it enters the focal region, the mission would begin the delicate work of using the Sun's lens. It would look back toward the Sun, block the solar disk with a coronagraph, and search for the faint Einstein ring containing light from the target exoplanet. This is the moment where the journey changes character. For years or decades, success means getting farther away. Then, suddenly, success means holding alignment, scanning carefully, and measuring subtle light patterns. The spacecraft becomes not a traveller rushing outward, but an astronomer standing at the edge of the solar system with one eye on the Sun. The focal line is not a station where the spacecraft stops completely. Spacecraft do not stop in space in the everyday sense unless they spend fuel to alter their motion. A probe moving outward will continue moving. This may actually be useful because different distances along the focal line can sample different aspects of the lensed light, but the mission must manage its motion carefully. It may need to adjust sideways across the image plane, moving not huge distances by planetary standards, but enough to sample different pixels of the projected image. The target planet itself is moving around its star. The spacecraft is moving away from the Sun. Earth is moving. The Sun is moving through the galaxy. Nothing in this arrangement is truly still, although mission diagrams often make things look calm and tidy, because otherwise everyone would need a nap. The image reconstruction would depend on data gathered over time. The spacecraft might measure brightness and spectra at many locations, gradually building the information needed to recover a two-dimensional image. If the target planet rotates, the data changes. If clouds move, the data changes. If the planet has seasons or weather, the data changes. This is both a complication and a treasure. A static image would be amazing, but a changing world is even more informative. Repeated observations might reveal rotation rate, cloud patterns, surface contrast, maybe even climate behaviour. The long journey would not end in one photograph. It would open a long act of watching. Because of the travel time, the mission would also require a different kind of human patience. A spacecraft launched by one generation might return its most important results to another. Scientists who helped design the mission may not be the same people who analyse the final reconstructed images. Students may become senior researchers while the probe is still coasting outward. Children alive at launch may be adults when the first detailed alien planet image appears. There is something sobering and lovely about that. Some scientific projects are longer than the individual careers. They ask a civilization to cooperate with its future self. They ask us to begin something not because we will personally see every reward, but because someone should. This is not unusual in astronomy. Light itself teaches us long patience. When we look at a galaxy millions of light years away, we see it as it was millions of years ago. When we study the cosmic microwave background, we look back almost to the beginning of the universe. Astronomy is already a conversation across time. A solar gravitational lens mission would bring that long timing into engineering. We would launch a machine into the outer dark, wait through years of silence and signals, and trust that the slow work matters. It is science as a relay race, except the baton is a spacecraft hundreds of astronomical units away, and the finish line is a picture of a planet around another star. The journey also changes how we think about the edge of the solar system. For a long time, the outer solar system has felt like a boundary, the place where sunlight weakens, planets end, and interstellar space begins. But if the solar gravitational lens becomes useful out there, then the edge becomes an instrument platform. The distant hundreds of astronomical units are not merely empty, they are where certain kinds of seeing become possible. The cold outskirts become valuable real estate for astronomy. Future maps of the solar system may not only mark planets, moons, asteroid belts, and Kuiper belt objects. They may mark focal lines for nearby stars, communication corridors, observatory paths, and slow streams of probes heading outward like seeds on a stellar wind. There is something practical and almost domestic about choosing the right line. Suppose humanity wants to image a planet around Proxima Centauri. The spacecraft must travel in the direction opposite Proxima from the Sun. If we choose another target in another part of the sky, the required line points elsewhere. Over time, if we wanted to image many worlds, we might send many missions in many directions. The solar system would grow a faint invisible architecture of purpose. Probes scattered far beyond the planets, each using the Sun to study a different star system. From the outside, if anyone could see it, humanity's home system might look like a quiet star surrounded by tiny instruments at enormous distances, all staring back toward the light that sent them. That future is not near in the ordinary sense. It depends on technology, funding, mission priorities, and the continued desire to answer questions that are not useful in the immediate way a toaster is useful. But human beings have always made room for this kind of usefulness. We build observatories because knowing where we are matters. We send probes because seeing directly changes us. We study distant planets because a universe full of worlds is different from a universe where worlds are rare. The long journey to the solar gravitational focal line would be expensive, difficult, and slow, but it would be aimed at one of the oldest human wishes, to see what is beyond the horizon. For most of history, the horizon was a hill, a sea, a forest edge, a mountain pass. Then it became the atmosphere, then the moon, then the outer planets. Now, in this story, the horizon is not a place where land ends. It is the limit of our resolution, the boundary between a planet as a dot and a planet as a world. To cross that boundary, we may need to send small machines farther than any telescope has ever gone, to a region where the Sun is both behind them and at the centre of their work. They will not find a platform waiting there. They will create an observatory by arriving at the right distance, in the right alignment, with the right instrument still alive after a journey through almost unimaginable emptiness. Far beyond the planets, where the Sun has shrunk to a fierce bright star, and Earth has disappeared into the direction of home, the greatest telescope in human history may not look very great at all. It may not be a grand observatory with a wide mirror, golden panels, and the proud posture of a machine that knows it will be placed on posters. It may not resemble Hubble or James Webb, or the huge ground-based telescopes that sit on mountaintops under dry, careful skies. It may be small, it may be light, it may be one member of a fleet. It may look almost fragile, like a clever folded insect made from reflective film, carbon fibre, antennas, sensors and stubbornness. And if it uses a sail, it may have crossed the solar system not by carrying a mountain of fuel, but by letting sunlight push it gently, steadily, for years. This is one of the more surprising turns in the story. To use something as enormous as the sun's gravitational lens, we may need spacecraft that are not enormous at all. The lens is already huge. The sun provides the mass. The solar system provides the distance. Curved space-time provides the optical power. What the spacecraft needs to do is reach the right place, survive the trip, make careful measurements, and send the data home. That does not necessarily require a giant vehicle. In fact, giant vehicles can become a problem. Large spacecraft are expensive to launch, difficult to accelerate, and risky to send on journeys where repair is impossible. A smaller craft, if designed well, can be launched more easily, pushed more efficiently, and perhaps sent in groups, so that the mission does not depend on one lonely machine doing everything perfectly for decades. Solar sails fit naturally into this idea because a sail works best when mass is low. A sail is pushed by light, not by solar wind, though that phrase is often used casually and can cause some confusion. The solar wind is a stream of charged particles flowing from the sun, and there are concepts that use that too. But a classic solar sail is pushed mainly by photons, by sunlight itself. Photons carry momentum. When they strike a reflective sail and bounce away, they transfer a tiny amount of momentum to the spacecraft. Each push is minuscule. If you stood under sunlight on Earth, you would not feel it shove you across the garden, which is probably for the best. Picnics would be very difficult if sunlight kept sliding everyone gently into the hedge. But in space, with a large enough sail and a small enough spacecraft, that tiny pressure can matter. It keeps pushing. It does not need fuel tanks. It does not run out in the ordinary way. As long as the spacecraft remains in sunlight, the push is there. The trick is patience and lightness. Rockets produce strong thrust for a limited time. They burn propellant, change speed, and then coast. A solar sail produces weak thrust for a very long time. It is a different style of travel, more whisper than shout, more continuous nudge than dramatic kick. A rocket says, "Go now." A solar sail says, "Keep going." For many missions, especially where quick acceleration is needed, rockets are still essential. A solar sail does not lift itself from Earth. It needs a launch vehicle to reach space. But once free of Earth's atmosphere and gravity, well, a sail can begin doing something rockets cannot do without using fuel. It can keep changing the spacecraft's path using sunlight. For a mission to the solar gravitational focal region, this matters because the destination is so far away. The craft must reach hundreds of astronomical units. If it crawls outward at the pace of older probes, the mission takes too long. If it is very light and can gain high speed from a close solar pass, the time becomes more reasonable. Some concepts imagine small sailcraft first falling inward toward the sun, approaching close enough that sunlight is far stronger than it is near Earth. Sunlight intensity increases sharply as you move closer to the sun. Near Earth, the solar push is gentle. Near the sun, it becomes much stronger, and a well-designed sail could use that intense light to accelerate outward rapidly. The spacecraft dives inward, swings near the star, catches the light at its strongest, and then heads outward on a fast escape path. It is almost like using the sun as a launch partner, though the sun is not aware of this arrangement and does not send a thank you card. This maneuver asks a great deal from the spacecraft. It must survive the heat of a close solar approach. Its sail must remain reflective and stable. Its materials must tolerate intense radiation and temperature changes. Its guidance system must control the sail angle precisely. If the sail is too heavy, the push is not enough. If it is too flimsy, It may wrinkle, tear, or twist. If it cannot deploy properly, the mission could fail before the long journey begins. A sail for this kind of mission would be a delicate balance between extreme thinness and reliable strength. That is a hard balance to achieve. Engineers do not get to build with wishful thinking. Materials have limits. Structures vibrate. Hinges stick. Films crease. Tiny flaws become serious when the system has to unfold in space and then work for decades. And yet, this is not pure fantasy. Solar sailing has already moved from idea to demonstration. Small sail missions have shown that sunlight can be used for propulsion and control. NASA's Advanced Composite Solar Sail System, known as ACS-3, is a technology demonstration aimed at testing deployable structures and materials that could support future solar sails. NASA describes the idea with a simple comparison. Just as a sailboat is powered by wind in a sail, a solar sail uses the pressure of sunlight for propulsion. That comparison is gentle and useful, though of course space has no ocean, no waves, and no sailor leaning back with one hand on a rope and the other hand on a cup of coffee. The deeper point is that a sail can travel by interacting with a natural flow of momentum. On Earth, that flow is air. In space, it can be light. A future solar gravitational lens mission would likely need something much more capable than a small demonstration in Earth orbit. It would need a sail system designed for speed, precision, and survival. The spacecraft itself might be modular. Instead of one large machine carrying every instrument and system, several small craft could launch separately and assemble, coordinate, or operate as a distributed mission. Some concepts imagine swarms of small spacecraft travelling together or arriving over time. That may sound untidy, but it has advantages. If one craft fails, others may continue. Multiple craft can sample different parts of the image region. They can provide redundancy, compare measurements, or serve as communication relays. Space missions often feel safer when there is not just one basket, especially when the basket is hundreds of astronomical units away and moving through darkness with no possibility of a technician tapping it gently with a wrench. A tiny spacecraft does not mean a simple spacecraft. In many ways, small machines must be more clever. They have less room for power systems, antennas, shielding, propulsion, computers, and instruments. Every gram matters. Every surface may have several jobs. A panel might support structure, reflect heat, carry wiring, and help with communication. A sensor might need to be small but exquisitely sensitive. A computer must be efficient but reliable. The spacecraft must protect itself from radiation, temperature extremes, dust impacts, and the slow wear of time. It must handle long periods without immediate human guidance. It must notice problems, correct them if possible, and keep the mission alive. A small deep spacecraft is not a toy. It is a folded argument that careful design can do what brute mass cannot. Power is one of the most serious problems beyond the planets. Near Earth, solar panels are convenient. Around Mars they still work, though with less sunlight. Farther out, around Jupiter and beyond, solar power becomes harder, and missions often use nuclear power sources. At 550 astronomical units, sunlight is extremely weak. A solar sail may have used sunlight for propulsion early in the journey, especially close to the Sun, but once the spacecraft is in the focal region, ordinary solar panels would not provide much energy. The probe would likely need a long-lived power source, perhaps radioisotope power, or another system capable of running instruments and communication far from the Sun. It needs enough energy to stay warm, operate detectors, process data, store information, point antennas, and make small course corrections. The Sun may be the telescope, but the spacecraft still has to keep itself alive in the cold. Communication also becomes a careful art. A small spacecraft, hundreds of astronomical units away, must send signals back to Earth across a distance so large that even light needs days to travel it. The signal spreads out as it moves, becoming extremely faint. On Earth, large antennas would have to listen with great sensitivity. The spacecraft would need to aim its transmitter accurately. A tiny pointing error over such a distance can matter, and because the spacecraft is looking back toward the Sun to observe the Einstein ring, communication geometry may be awkward. It has to manage where it points, when it observes, when it transmits, and how much data it can send. A high-resolution reconstructed image of an exoplanet may require enormous amounts of measurement data. The spacecraft cannot simply take one pretty picture and email it home with the subject line, "You may want to sit down." The craft must also navigate after arrival. This is easy to miss. We might imagine the probe racing outward, reaching 550 astronomical units, and then relaxing as if it has arrived at a hotel. But there is no hotel. There is no platform. There is no parking orbit around the focal line. The spacecraft is moving. The target planet is moving. Earth is moving. And the Sun itself is travelling through the galaxy. The focal region is a place defined by alignment, not by an object. To image the target, the spacecraft must scan across the projected image area, making measurements from many positions. That means it needs some form of fine manoeuvring, perhaps small thrusters, perhaps sail trimming earlier in the mission, perhaps electric propulsion. The exact method depends on the architecture, but the principle is clear. Arriving far away is not enough. The probe must work far away. This is where tiny spacecraft and large ambition meet. The spacecraft may need a small onboard telescope, perhaps meter class in some mission studies, along with a coronagraph to block the Sun's bright disk. It must observe the faint Einstein ring around the Sun, separating the exoplanet signal from solar corona, background stars, instrumental noise, and light from the exoplanet's host star. The instrument does not need to be the largest telescope ever launched, because the Sun's gravity is doing the heavy optical lifting. But it must be stable, precise, and very well understood. A small error in measurement could ripple into the reconstructed image. When your data comes from a faint ring of light around the Sun, you want the instrument to be less moody than the average printer. Autonomy becomes essential. At 550 astronomical units, a one-way light time of more than 3 days means human operators cannot joystick the spacecraft in real time. If something happens, the spacecraft cannot wait for Earth to notice, discuss, hold a meeting, write a command sequence and send it back a week later. It needs onboard decision-making. It needs fault protection. It needs to handle safe modes and recoveries. It needs to know where it is, where the Sun is, where Earth is, and how to keep its instruments pointed. It may need to process data on board before sending it home, because raw data volumes could be large and transmission rates low. Deep space autonomy is not a luxury here. It is survival. There is a quiet comparison to be made with older spacecraft. Voyager, Pioneer, New Horizons, Cassini, and other missions were and are remarkable, but they were built in a tradition of large, carefully managed spacecraft with powerful ground support. A solar gravitational lens mission may lean toward a newer style, smaller, more numerous, more autonomous, perhaps launched in waves. This does not make it easier, but it changes the shape of the challenge. Instead of one cathedral-like observatory, we might send a fleet of little scouts, each one small enough to accelerate quickly, smart enough to operate alone, and specialized enough to perform one part of a larger task. It is the difference between building one giant ship and releasing a group of highly disciplined messenger birds into the dark, though the birds in this case need radiation shielding and advanced optical systems. The sail itself may not remain useful forever. Once the spacecraft has gained speed and moved far from the Sun, the sunlight becomes too weak to keep accelerating it significantly. The sail might be jettisoned, folded, repurposed, or simply carried along depending on design. If it remains attached, it could affect pointing and stability. If released, the spacecraft becomes smaller and easier to handle. Mission designers would have to decide whether the sail is only a launch and acceleration tool or part of the long-term spacecraft. A sail near the Sun wants to be large and reflective. An observatory hundreds of astronomical units away wants to be stable, pointed, and thermally controlled. Sometimes one machine cannot be perfectly suited to every phase, which is why modular designs become tempting. A close solar pass adds another layer of drama, though the narration should not get too excited this late in the evening. To accelerate effectively, the sailcraft may pass very close to the Sun. That requires a heat shield or materials that can survive intense solar radiation. NASA's Parker Solar Probe has already shown that spacecraft can operate remarkably close to the Sun using advanced thermal protection, though Parker is not a solar sail. A sailcraft would face different constraints because its sail must be exposed to sunlight, not hidden behind a shield. It must reflect most of the incoming energy rather than absorb it. Any absorption becomes heat, and too much heat becomes failure. The sail must be bright in the literal sense, reflecting sunlight efficiently, and durable in the engineering sense, keeping its shape when the Sun is doing its best impression of a cosmic furnace. After the push near the Sun, the journey outward would be long and mostly quiet. The sailcraft would leave the inner solar system at high speed. The planets would become milestones behind it. Jupiter might pass in the data as a distant giant. Saturn's orbit would be crossed. Uranus and Neptune would fall behind. Then the craft would enter the long emptiness beyond the planets, where there are icy bodies, dust, cosmic rays, and the fading influence of the solar wind. It might cross the region where the heliosphere gives way to interstellar space. The Sun's light would weaken. The spacecraft would continue outward, coasting through decades, checking its systems, correcting its path, and waiting for the geometry ahead to become useful. It is tempting to think of such a spacecraft as lonely. We tend to humanize machines that travel far from home. Voyager feels lonely. Opportunity felt brave. Cassini felt noble. A tiny sailcraft heading to the solar gravitational lens would feel almost like a message in a bottle, except the bottle has a flight computer and a very specific job. But loneliness is our feeling, not the spacecraft's. The probe does not mind the dark. It does not miss Earth. It does not worry about being forgotten. Its success lies in function. It has to survive, align, observe, and transmit. Still, the human meaning of the mission is hard to ignore. We would be sending a small piece of our curiosity farther than almost anything we have ever built, not to land on a planet, not to sample ice, not to orbit a moon, but to stand in a place where the Sun's gravity can help us see another world. The scale of that contrast is beautiful in a practical way. A little craft, perhaps no larger than a suitcase or a small appliance in some designs, travels hundreds of astronomical units to use a star as an optical instrument. The detector is small, the lens is enormous, the machine is fragile, the idea is vast. The spacecraft is built in clean rooms, tested with procedures, packed into a launch vehicle, and sent through a series of carefully timed events. The lens it uses was made by gravity 4.6 billion years ago, with no paperwork whatsoever. This partnership between tiny engineering and giant nature is at the heart of the solar gravitational lens mission. Small spacecraft could also change how often we attempt such missions. A single enormous observatory is a rare event. It may take decades to fund, build, launch, and operate. A fleet of smaller sailcraft, if the technology matures, could be produced more regularly. Perhaps one leaves every year or every few years, each aimed at a different focal line. One toward a planet around Proxima Centauri, another toward a promising world around Tau Ceti, if future observations make such a target compelling, another toward a nearby red dwarf system. Over time, the outer solar system could become populated by distant robotic observers, all using the Sun in different directions. The idea feels futuristic, but not absurd once the first path is proven. Many technologies begin as one difficult mission and later become a repeatable method. There is also the possibility that the spacecraft will need to cooperate with instruments closer to home. Earth-based and near-Earth telescopes would continue monitoring the target planet and star. They would refine the orbit. They would watch for stellar flares, especially around red dwarfs. They would provide context for the distant probe's data. If a planet's brightness changes, is it a cloud system, a rotation effect, a stellar variation, or an instrument issue? The best answers may come from combining data across many observatories. The little sailcraft far away would not work alone in a scientific sense. It would be the farthest member of a larger observing network. The mission would also be built on trust in software. The reconstruction of an exoplanet image from solar gravitational lens data is not a simple act of looking. It is a computational process. The spacecraft gathers brightness measurements from many positions. The data is shaped by the lensing geometry, the instrument response, the solar corona, and the planet's own motion. Algorithms then try to recover the planet's image. That means the mission depends not only on hardware, but on mathematical care. Scientists would test reconstruction methods on simulations, laboratory data, and perhaps observations of known objects before trusting them with an alien planet. The final image would not be a casual snapshot. It would be a carefully reconstructed result, with uncertainties, checks, and probably many arguments in conference rooms. This is how science keeps itself honest, even when the dream is enormous. Because the spacecraft are small, they may have limited shielding. Dust impacts become a concern over long distances. A tiny grain moving at high relative speed can damage sensitive surfaces. Electronics can degrade under radiation. Mechanical parts can seize after years of cold. Lubricants behave differently in vacuum and low temperatures. Materials age. Memory bits flip. Antennas drift out of alignment. A deep space mission is less like building a machine and more like raising a machine for a long, difficult life. You have to think about what happens after 10 years, 20 years, 30 years. You have to imagine failures before they happen and give the spacecraft ways to endure them. The farther it goes, the more it must become its own caretaker. There is something very fitting about using small craft for this job. Exoplanets themselves are hidden by scale. They are too small and faint beside their stars. To see them, we use the largest thing available to us, the sun's gravity. But to reach the place where that giant lens works, we may use some of the smallest serious spacecraft we can build. The mission stretches from the tiny to the enormous, a thin sail catching photons, a probe crossing the outer dark, a star bending space-time, a planet circling another sun. A reconstructed image arriving at Earth after years of work. Each scale depends on the next. The universe is not one size of problem, it is all sizes at once. As the sailcraft moves beyond the planets, it also moves beyond the familiar emotional boundary of exploration. Planetary missions usually have visible destinations. Mars has a disk, Jupiter has bands, Saturn has rings, Pluto had a heart-shaped plane waiting in the dark. A solar gravitational lens spacecraft does not travel to see the place it visits. It travels to use that place as a viewpoint. The destination is not the subject. The subject is behind the sun from the spacecraft's perspective, many light years farther away. This is a subtle shift. The spacecraft goes far out not because far out is itself the object of study, but because far out gives the right line of sight. It is exploration as positioning. When the probe finally begins its work, the sail that carried it may be long gone, folded, quiet, or drifting separately. The heroic part will not look heroic. No flames, no landing, no cheering over touchdown. Yet the most important part of the mission would not be the travel itself. The journey is only the long walk to the doorway. The real work begins when the spacecraft turns back toward the sun and tries to turn bent starlight into a picture of another world. That sounds At first, almost simple. Light from an alien planet passes near the sun. The sun's gravity bends and focuses it. A spacecraft waits far away, catches the focused light, and makes an image. There we are, a cosmic camera, a planet around another star, a picture for the history books. Perhaps someone prints it, frames it, and hangs it next to the first image of the Earth from space. But nature rarely gives us the simple version of anything, especially when stars, gravity, optics, and interstellar distances are involved. The solar gravitational lens does not behave like an ordinary camera lens. It does not form a neat little picture on a detector, with the planet politely arranged as a tiny disk, oceans on the left, clouds on the right, and maybe a small mysterious continent in the middle, waiting to cause a scientific argument. Instead, the light is bent around the sun and appears as a thin ring, or nearly a ring, around the solar disk. The planet's information is there, but it is wrapped, smeared, mixed, and hidden inside that ring. This ring is called an Einstein ring, and it is one of the more beautiful ideas in gravitational lensing. If the alignment between the distant source, the lensing mass, and the observer is very good, light from the background object can be bent around the foreground mass in all directions, forming a ring of light. In the case of the solar gravitational lens, the foreground mass is our sun. The background source is the distant exoplanet, or more precisely, the light reflected or emitted by that exoplanet. The observer is the spacecraft, waiting hundreds of astronomical units away. The ring would appear very close to the sun from the spacecraft's point of view, which is why the spacecraft needs a coronagraph to block the sun's bright disk and help reveal the faint signal near the glowing corona. Now, if this were an ordinary photograph, the spacecraft could simply take a picture of the ring, send it back, and scientists would admire it while drinking too much coffee. But the ring itself is not the final picture. The ring is more like a scrambled envelope containing the picture. Each part of the exoplanet contributes light to the ring. Light from its oceans, clouds, deserts, ice, or whatever else it has is bent by the sun's gravity and distributed in a complicated way. The image of the planet is not lost, but it has been transformed. Recovering it requires knowing how the solar gravitational lens changes the light, then undoing as much of that change as possible through mathematics. This process is often called deconvolution, which is a word that sounds as if it was designed to make people gently close their laptops. But the idea is not too mysterious. If a system blurs an image in a predictable way, and you understand the blur, you can try to reverse it. A simple example might help. Imagine looking at a landscape through frosted glass. You can still see brightness and colour, perhaps the rough shape of a tree or the glow of a window, but the details are smeared. If you knew exactly how the glass smeared every point of light, and if your measurements were very good, you could use mathematics to recover some of the original structure. You would not be creating detail from nothing. You would be extracting detail that was still present in the blurred signal. The solar gravitational lens does something far more complex than frosted glass, but the basic spirit is similar. The sun's gravity transforms the planet's light in a known physical way. The spacecraft measures that transformed light. Then scientists use models of the lens to reconstruct the original planet. Of course, the word known carries a lot of responsibility here. The sun's gravitational field is very well understood, but real observing conditions are messy. The sun has a corona, and the corona glows. The spacecraft's detector has noise. The telescope has its own optical imperfections. The target planet rotates. Clouds move. The planet orbits its star. The star itself may flare, especially if it is a red dwarf like Proxima Centauri. The spacecraft is moving too. Nothing sits still like an obedient drawing in a textbook. A real imagery recovery system must account for all of this. It must separate planet light from solar background. It must know where the spacecraft is with great precision. It must measure the ring carefully. It must understand how each measurement relates to the surface of the planet. and then it must build the picture one piece at a time. This is why the phrase "one pixel at a time" matters. A spacecraft using the solar gravitational lens would not necessarily capture the entire exoplanet image all at once. Instead, it may need to scan across the projected image region, taking measurements from many positions. Each position gives information related to a small part of the final reconstructed image, though not in a perfectly simple way. The spacecraft might move sideways across a narrow region of space, sampling light at one point, then another, then another. Each measurement is like dipping a tiny cup into a vast river of bent light and asking what part of the distant world is hidden in that cup. Do this enough times, with enough precision and enough patience, and a map begins to emerge. The image plane near the solar gravitational focal region is strange because enormous distances are compressed into manageable scales. The distant planet may be thousands of kilometers across, but its projected image through the solar gravitational lens can correspond to a much smaller pattern that the spacecraft can scan through. This is part of the magic of the geometry, but it also means the spacecraft must know where it is inside that pattern. A small movement in the image plane may correspond to a large shift on the exoplanet's surface. If the spacecraft is trying to build a 1,000,000-pixel image, it must gather enough samples, know their locations, and account for the way the lens mixes the light. It is less like taking a holiday photograph, and more like assembling a planet-sized mosaic from light that has been folded around a star. The first reconstructed images would probably not look perfect. That is important. We should not imagine that the first attempt will reveal a crisp alien globe, like something from a polished science fiction poster. It may begin as a rough map. There may be noise, artifacts, missing information, uncertain features, and cautious labels. Scientists may spend months or years arguing about whether a bright patch is cloud, ice, instrument noise, or a reconstruction effect. This is normal. The first images from new kinds of instruments often require careful interpretation. Early radio maps of the sky did not look like the sharp space images we're used to today. Early planetary photographs were grainy and strange. Even images from modern telescopes depend on calibration, processing, and interpretation. A reconstructed exoplanet image from the solar gravitational lens would be one of the most processed scientific images ever made, and that does not make it fake. It makes it honest about the difficulty of seeing. In fact, almost every astronomical image is a translation. A telescope gathers light in certain wavelengths. Detectors convert photons into signals. Software removes noise, corrects distortions, combines exposures, assigns colours, and sharpens structure. When we look at a beautiful image of a nebula, we are not seeing it as a human eye would see it from a nearby spaceship window. We are seeing a careful scientific translation of light into something our eyes and minds can understand. The solar gravitational lens would simply take that act of translation to an extreme. The raw signal is a ring around the sun. The final result is a map of another planet. Between them lies physics, computation, and a great deal of restraint. Restraint matters because reconstruction can mislead if handled badly. When data is noisy or incomplete, algorithms can sometimes invent patterns or exaggerate weak features. This is not because computers are mischievous, though anyone who has watched a software update fail at the worst possible moment may suspect otherwise. It is because image recovery is a delicate mathematical problem. You're trying to infer the original scene from measurements that have been blurred, mixed, and contaminated by noise. To do that responsibly, scientists use regularization, validation, simulations, and independent checks. They ask whether the same feature appears in different wavelengths. They test whether it persists over time. They compare reconstructions using different assumptions. They try to prove that the image is not just what they hope to see. Before such a mission ever looks at a real exoplanet, researchers would test the methods with simulations. They might take images of Earth, treat Earth as if it were a distant exoplanet, pass that image through a model of the solar gravitational lens, add realistic noise from the solar corona and instruments, and then try to reconstruct the original. This is a sensible way to practice, because Earth is the one habitable planet whose appearance we know well. If the reconstruction can recover continents, oceans, clouds, and polar regions from simulated lensed data, then the technique becomes more believable. If it fails, the failure teaches engineers and scientists what must improve. In this way, Earth becomes both the example and the test answer hidden at the back of the cosmic workbook. One study has suggested that, under realistic assumptions, a high-quality 1,000 by 1,000 pixel image of an Earth-like planet near Proxima Centauri could be obtained with an integration time on the scale of months. That does not mean the result would be easy, guaranteed, or free from uncertainty. It means the physics and observing strategy may be feasible enough to take seriously. 1,000 by 1,000 pixels sounds small compared with modern phone cameras, which casually produce images with millions of pixels while also somehow making dinner look worse in low light. But for a planet around another star, 1,000,000 pixels would be revolutionary. It would be enough to see large-scale structure. It could turn a world from a point into a disk with geography. What would each pixel mean? Not a city block, probably. Not a tree or a house, or a person waving up at the sky, unless the universe is much stranger and more theatrical than expected. A pixel might correspond to tens or hundreds of kilometers, depending on the target, distance, mission design, and reconstruction quality. That is still extraordinary. On Earth, hundreds of kilometers is enough to distinguish continents from oceans, major ice sheets, broad cloud systems, deserts, large mountain regions, and perhaps the changing edge of seasons. You would not see a village. You might see the planet's face. Colour would be just as important as shape. A grayscale map could reveal brightness patterns, but different wavelengths tell different stories. Blue light, red light, infrared light, and spectral features could help identify clouds, ice, ocean reflection, land surfaces, atmospheric gases, or thermal patterns. A planet with oceans might reflect light differently from a dry, rocky planet. Ice caps might be bright in visible wavelengths. Vegetation, if it exists, and if it has a reflectance feature somewhat like Earth's red edge, might leave a clue in the spectrum, though alien life need not use the same pigments or behave politely for our instruments. Infrared observations might reveal heat distribution, especially on a tidally locked planet where one side always faces its star. The image is not only where things are, but how they shine. The spacecraft might also watch the planet change. If it can observe over days, weeks, or months, it may see rotation. Bright and dark regions would move across the visible face. Clouds would form, drift, and dissolve. Ice might remain near poles, oceans might glint under certain angles. Storm systems might appear as shifting white patterns. If the planet has seasons, longer observations could reveal changes over its year. This turns imaging into climate study. A single image says, here is what the planet looked like. A series says, here is how the planet behaves. And behavior is often where worlds become interesting. Imagine Earth observed this way from far away. At first, the reconstruction might show a blue and white planet with broad brown-green land masses. Over time, the pattern rotates. Africa appears, then the Atlantic, then the Americas, then the Pacific. Clouds swirl and obscure the surface. The poles stay bright. Seasonal snow shifts. Ocean glint appears and disappears. A patient observer could learn that Earth has oceans, continents, weather, rotation, seasons, and a reflective atmosphere. They might not know our names, our languages, or the fact that we sometimes spend 10 minutes looking for a phone already in our hand, but they would know Earth is a complex world. Now reverse the situation. We are the distant observers. We are the ones watching light that left an alien world years ago and came to us bent around the sun. The planet may be around a red dwarf, where the star is smaller and cooler than the sun. It may be tidally locked, with permanent day on one side and permanent night on the other. It may have a thick atmosphere that moves heat around the globe. It may have clouds concentrated near the substellar point, the place where the star hangs overhead without moving. It may have ice on the night side, or winds so steady they shape the climate into patterns we have never seen. Turning the lens light into an image would not only reveal what is there, it would teach us how planets behave under conditions different from Earth. The reconstruction process would likely involve both science and caution. Suppose the first image shows a dark region that returns every rotation. Is it an ocean, a basalt plain, a deep atmospheric feature, or an artifact of the reconstruction? Suppose a bright region stays near one pole. Is it ice, cloud, salt flats, or haze? Suppose the planet shows patches that change with seasons. Is that life, snow, dust, vegetation-like chemistry, or something else entirely? The data would invite interpretation, but science must not leap too quickly. The first true pictures of exoplanets would be emotionally powerful, and that emotional power could tempt people toward dramatic conclusions. The careful path would be slower. Measure, compare, test, repeat. Let the planet become known by evidence, not by wish. Still, even cautious evidence can be breathtaking. The first time a reconstructed exoplanet image shows a stable ocean-like region, it would change how people feel about the night sky. The first time we see cloud systems on another rocky world, weather becomes a galactic concept, not just an earthly one. The first time we see a polar cap around another star, winter becomes something shared by planets beyond the sun. These are not small changes in perspective. They take familiar parts of Earth and show us that they may belong to a much larger family of worlds. Or just as interestingly, they may show us planets that look nothing like home at all. There is also the problem of the planet's host star. Many nearby potentially habitable planets may orbit red dwarfs. Red dwarfs are small and common, but they can be active. They can flare, blasting their planets with radiation and changing brightness. If a target star flickers or flares during observation, that affects the planet's light. A flare might brighten the planet temporarily or change the spectrum. The observing system must distinguish planetary features from stellar behavior. That means monitoring the star, perhaps with other telescopes, while the distant spacecraft observes the lens planet. Again, the Solar Gravitational Lens mission becomes part of a network. The FAR probe gathers the most detailed spatial data, while other observatories provide context. The Sun's corona remains one of the main local obstacles. The Einstein ring appears near the Sun, inside or against the glow of the solar corona. The corona is not a smooth, unchanging background. It has structure, streamers, and variations linked to solar activity. If the corona is bright or unstable, it can hide or contaminate the faint signal from the exoplanet. A spacecraft may need to observe at wavelengths where the signal is more favourable, use a coronagraph, wait for calmer conditions, model the coronal background, and subtract it carefully. It is strange to think that to see a planet around another star, we must first understand the outer atmosphere of our own. The road to alien geography passes through solar weather. The final image, when it comes, may arrive slowly. Not as one dramatic download, but as data over time. At first, perhaps there is no recognizable planet, only measurements. Then a rough reconstruction. Then a better one. Then corrections. Then colour. Then uncertainty maps. Scientists might release a cautious first version, with all the caveats lined up like sensible shoes at the door. Later, improved processing might sharpen it. More data might confirm or revise features. The first image of another Earth-like world may not be one moment, but a gradual unfolding, a planet becoming visible by degrees. That gradual unfolding fits the nature of the mission. Everything about the solar gravitational lens is slow and precise. The light travels for years from the exoplanet to the Sun. It bends around the Sun in a tiny curve shaped by gravity. It reaches a spacecraft hundreds of astronomical units away after a journey through dark space. The The spacecraft samples it position by position. The data crawls home at light speed over days. Computers reconstruct the image. Humans interpret it. There is no hurry built into this process. It is a long conversation with a distant world, spoken in photons and answered in pixels. And perhaps that is part of why the idea feels so meaningful. We live in a time when images are immediate, disposable, and endless. A phone can take 1,000 photographs in an afternoon. But an image made with the sun as a gravitational lens would be different. It would be earned. Every pixel would carry the history of a journey, from the surface or atmosphere of another planet, across interstellar space, past the curved gravity of our sun, into the detector of a tiny faraway craft, through the silence to Earth, and finally into a human mind. A single pixel might contain light reflected from an alien ocean. Another might contain cloud. Another might contain ice. Another might contain a mistake that scientists spend 6 months arguing about, because even in the future, science will remain science. The phrase rebuilding an alien planet should not be taken too literally. We are not reconstructing the planet itself, only an image of its light. But in human understanding, images matter. They help turn data into place. They let us compare, recognize, question, and remember. A planet that has been only a line in a catalogue becomes a face. It gains a visible presence in our imagination. Children might grow up knowing the first few imaged exoplanets the way people today know Mars or Jupiter. Not as mythology, not as guesses, but as worlds with observed patterns. As the spacecraft continues scanning, the picture would improve. More samples mean better reconstruction. More wavelengths mean richer interpretation. More time means the chance to watch motion. The mission might begin with one target and spend years studying it. It might map the planet at different orbital phases. It might search for changes that suggest seasons. It might compare dayside and nightside if the geometry allows. It might build not just a portrait, but a small atlas. The first atlas of a world around another star would be one of the most remarkable documents humanity has ever made, even if it begins as a grid of uncertain colours and carefully labelled confidence levels. So the bent light around the sun becomes more than a ring. It becomes a puzzle that can be solved, not perfectly, not easily, but enough to reveal something real. The spacecraft does not see the alien planet directly in the ordinary sense. It sees the planet through the sun's gravity. It reads a message written around a star. It moves, samples, measures, and sends home pieces. On Earth, those pieces become pixels. The pixels become patterns. A world that was once only a dip in starlight begins to take shape. What might we actually see? Once the bent light has been measured, sorted, checked, corrected, argued over, reconstructed, and finally shaped into something like an image, the question changes. It is no longer only, can we see another world? It becomes, what will that world look like when it finally stops being a dot? That is the moment where the science becomes almost uncomfortably human. Because the first true image of a rocky planet around another star would not just be a technical achievement, it would be a new kind of encounter. Not a landing, not a visit, not a conversation, but still an encounter. For the first time, a planet that has lived its whole life under another sun could show us a face. And what might be on that face? We should begin carefully. A solar gravitational lens image would not show tiny details in the way spy satellites can show streets on Earth. It would not show individual trees, animals, houses, boats, windows, or someone on an alien shore looking up with a cup of something warm and wondering whether anyone else is awake. The distances are too great, the reconstruction too complex, and the pixels too large for that kind of intimacy. Even with a powerful gravitational lens, we would be seeing large-scale features first. Planet-sized patterns, regional differences, broad contrasts, the kind of details that tell you whether a world has oceans, clouds, ice, deserts, seasons, and perhaps unusual patterns of light. That may sound modest until you remember that today, for most exoplanets, we do not even have that. We have shadows, wobbles, spectra, and dots. Turning those into a map would be like going from hearing a rumour about a country to seeing it from orbit. The most emotionally powerful feature would probably be oceans. Not because oceans are guaranteed, and not because every habitable world must look like Earth, but because oceans are one of the great signs of a planet with a rich surface environment. Liquid water matters for life as we know it. It shapes climate, chemistry, erosion, weather, and habitability. On Earth, the oceans make our planet bright and blue from space. They store heat, move energy around the globe, feed storms, dissolve gases, and cover most of the surface. If another rocky planet showed large dark blue or low reflectance regions that change with viewing angle, and if the spectrum supported liquid water, that would be one of the most important discoveries in astronomy. It would not prove life. A lifeless ocean is possible, but it would say, here is a world with a surface that can hold liquid, a world with a climate gentle enough, at least somewhere, for water not to be only ice or vapour. Detecting oceans from far away would not be as simple as looking for blue paint. Planet colours can mislead. A thick atmosphere can hide the surface. Clouds can cover oceans. Hazes can tint a planet. Minerals can reflect light in unexpected ways. A planet around a red dwarf would be lit by redder light than Earth receives from the sun, so its colours would not match our familiar mental picture. Ocean glint could help. Glint is the bright reflection that appears when light bounces off a smooth liquid surface at the right angle, the same effect that makes sunlight flash on a lake or sea. From space, Earth's oceans can produce glint, and scientists have studied whether similar glints might reveal oceans on exoplanets. But even that is tricky. Clouds can scatter light in ways that imitate some brightening effects, and atmospheres can hide the signal. The planet would not hand us a label saying, "Ocean here, please update textbooks." We would need multiple lines of evidence. Still, imagine the possibility. A reconstructed world slowly sharpens, and across one hemisphere there is a broad dark region that behaves like a sea. It reflects differently at different phases. It stays in place as the planet rotates. Its spectrum fits liquid water better than rock or ice. Clouds gather above it. Weather moves from it. Suddenly, the idea of an alien ocean stops being only a phrase. It becomes a region on a map. There might be waves there, though we could not see them. There might be storms drawing heat from it. There might be coastlines where liquid meets land, though the exact shore would blur across pixels. No one would know whether anything swims below that surface. But the discovery of an ocean on another world, seen rather than merely inferred, would make the galaxy feel different. Continents would be another kind of revelation. On Earth, land breaks the oceans into shapes that have become familiar to us, not only as geography but as history. Continents guide weather, they build mountains. They host rivers, deserts, forests, ice sheets, and cities. On an exoplanet, large landmasses might appear as brighter or differently coloured regions compared with oceans. They might rotate into view and disappear again. They might show seasonal changes if snow, vegetation-like surfaces, dust or frost come and go. A planet with both oceans and continents would be especially interesting because coastlines, shallow seas and cycles between land and water may create chemical variety. Earth's habitability is not just water. It is water interacting with rock, air, sunlight, and time. Continents are part of that long conversation. But there is no rule that alien continents must look like ours. A planet could be mostly ocean, with only scattered islands or no exposed land at all. It could be mostly land, with small seas or frozen basins. It could have one giant supercontinent, like Earth has had in its past, or several smaller land masses. It could have dark basaltic plains, bright salt flats, rust-coloured deserts, reflective ice-covered plateaus, or mineral surfaces with colours that do not fit our expectations. Around a cooler red star, photosynthetic life, if it exists, might not be green. It might use pigments better suited to different wavelengths of light, or it might not cover land in a way visible from space. A world could be alive and not look like a garden. A world could look dull and still be chemically fascinating. The first images may remind us that Earth is not the template for everything. It is one example. Clouds may be the first obvious feature in many images, and also one of the most annoying. Clouds are beautiful when you're lying in a field giving them names, and deeply inconvenient when you're trying to map a surface from several light years away. Earth is often cloudy. A snapshot of Earth can hide huge areas of land and ocean beneath white weather systems. For an exoplanet, clouds might cover even more. A thick cloudy planet could reveal little of its surface, at least in visible light. But clouds are not just obstacles, they are information. They reveal an atmosphere with circulation, condensation, temperature differences, and active weather. A planet with changing cloud patterns is a planet with moving air. If those clouds form in certain regions again and again, they can reveal climate structures. If they swirl into storms, they reveal rotation and energy. If they gather near the substellar point of a tidally locked world, they may help scientists understand how heat is distributed. A tidally locked planet deserves a moment here, because many nearby potentially habitable planets may orbit small red dwarfs. When a planet orbits close to such a star, gravity can slow its rotation until the same side always faces the star, much as the moon keeps the same face toward Earth. One side has permanent day, the other has permanent night. For a long time, people imagined such worlds might be hopeless, with one side scorched and the other frozen. But models suggest that a thick enough atmosphere and perhaps oceans could move heat around, creating more moderate conditions. If we could image such a planet, we might see a strange climate pattern unlike Earth's. Perhaps bright clouds near the point where the star hangs forever overhead. Perhaps ice on the night side. Perhaps a ring of more temperate conditions near the twilight zone between day and night. That would not be a familiar world, but it might still be a world with weather, chemistry, and maybe habitability. Ice caps would be among the easier large features to recognize if they are present and not hidden by clouds. Ice is bright in visible light, especially compared with ocean or dark rock. On Earth, the polar ice caps and seasonal snow cover help define the planet's appearance from space. On an exoplanet, stable bright polar regions could suggest ice, though again caution would be needed. Bright minerals, clouds, haze, or reflective salt flats could confuse interpretation. If the bright regions grow and shrink over time in a seasonal rhythm, the case becomes stronger. Seeing seasons on another planet would be astonishing. It would mean the planet's climate is not only present, but changing predictably as it orbits its star. Spring, autumn, freeze, thaw, cloud shifts, snow lines, all translated into distant pixels. There is something quietly moving about the idea of alien winter. Not poetic in a vague way, but concrete. On Earth, winter is a physical response to axial tilt, sunlight angle, atmospheric circulation, ocean heat, land distribution, and local geography. If another world has seasons, it has its own version of that machinery. Its poles may brighten and dim. Its atmosphere may shift. Its storms may migrate. Its surface may change colour. No person from Earth would feel the cold there, but the pattern would be real. The planet would have a year, not just as a number in a catalogue, but as a visible cycle. Weather systems might be the most dynamic part of the image. Clouds could move from one observation to the next. Storms could brighten and fade. Bands might form if the planet rotates quickly. A thick atmosphere could produce global haze or high reflective cloud decks. If the planet has oceans, storms may feed from warm water. If it is dry, dust storms may spread across continents. If it is tidally locked, winds may race between day and night. Weather would make reconstruction harder because the planet changes while the spacecraft is scanning, but it would also make the planet real. A world without change can feel like a painted sphere. A world with weather is doing something. It has a present tense. And then, very carefully, we come to the most tempting possibility: signs of technology, cities, lights, patterns that are not natural. This is where the imagination runs ahead fastest, and where science has to walk with both hands on the railing. The idea of seeing alien cities is powerful because it would mean not just life, but minds, societies, engineering, perhaps beings looking at their own sky. But detecting cities from interstellar distance would be incredibly difficult. Even the sun's gravitational lens would not simply show streets or buildings. At best, under favourable conditions, one might imagine detecting unusual night-side illumination, geometric patterns, artificial atmospheric compounds, waste heat, or other techno-signatures. NASA and other researchers discuss techno-signatures as possible evidence of technology beyond Earth, but these are speculative and challenging to detect. City lights on Earth are visible from space, but mainly from nearby orbit or from the Moon with sensitive imaging. From another star, Earth's artificial lights would be extremely faint compared with the reflected sunlight. You would usually want to look at the night side, but observing a planet's night side from far away depends on orbital geometry, phase, and contrast. A civilization may not use lights like ours. It may be underwater, underground, low energy, spread out, or long gone. It may deliberately avoid waste light, or it may have technology that produces signals unlike anything we would think to search for. The absence of visible cities would not mean absence of intelligence. It might simply mean our methods are not suited to their lives, or that their planet is not trying to make itself convenient for our documentaries. Even so, suppose a reconstructed planet showed a pattern that appeared only on the night side, remained fixed to the surface as the planet rotated, and had a spectrum unlike auroras, lightning, lava, reflected moonlight, or natural air glow. Scientists would become very cautious and very busy. The first explanation would not be alien cities. It would be instrument effects, solar corona subtraction errors, reconstruction artifacts, unusual atmospheric emissions, stellar contamination, natural glow, and anything else that could be tested. Extraordinary claims require extraordinary patience, but if a technological explanation survived every attempt to remove it, the discovery would change history. Not because we saw a skyline, but because the planet would show evidence of activity not easily explained by geology or weather alone. There are more subtle techno-signatures than lights. Certain atmospheric gases could suggest industrial processes if they are difficult to produce naturally and appear in suspicious combinations. Large artificial structures might affect reflected light or infrared emission, though detecting such things would be very hard. Waste heat from a highly energy-consuming civilization could change thermal patterns. Radio signals might be detected by other methods. A solar gravitational lens image could provide context for these clues. If a planet's atmosphere suggests unusual chemistry, and its surface map shows patterns that change in unexpected ways, scientists could combine evidence. No single clue needs to carry the whole burden. The strongest case would come from several independent signs pointing in the same direction. But we should not let cities steal the wonder from oceans, clouds, and ice. A lifeless planet with a global ocean would still be a wonder. A cloudy world with violent storms would still teach us something profound. A frozen planet with seasonal changes would expand our understanding of climate. An inhabited world with no technology would be one of the greatest discoveries in human history. Even microbial life, invisible to the image itself, could change an atmosphere, alter surface colours, or influence chemistry. The search for life does not begin with skyscrapers. It begins with conditions, cycles, gases, surfaces, and energy. A living planet might look quiet from far away. Earth itself was alive for billions of years before city lights appeared. In some ways, the first detailed exoplanet image might raise more questions than it answers. Imagine a planet with oceans but no obvious continents. Is it a water world? Does it have a rocky seafloor with hydrothermal vents? Could life arise without land? Imagine a planet with large land masses but no apparent oceans. Is water hidden underground, trapped as ice, or absent? Imagine a planet with bright clouds that never clear. Is it habitable below them, like a milder Venus, or hostile under crushing pressure? Imagine a world with one side bright and cloudy and the other dark and icy. Is there a habitable belt between them? Each image would be a beginning, not a conclusion. The first map would not say, "mystery solved." It would say, "here is a better mystery." The act of comparison would be unavoidable. We would compare every image world with Earth, Mars, Venus, Titan, Europa, and the planets we already know. That is natural. We understand new things through old things. But eventually the exoplanets would teach us their own categories. We might discover common planet types that do not exist in our solar system. We already know from exoplanet surveys that the galaxy makes many super-Earths and mini-Neptunes, worlds between Earth and Neptune in size, even though our solar system has none. Detailed imaging might reveal climates and surfaces with no local example. A planet could have reflective mineral plains that mimic ice, or clouds made from unexpected chemistry, or global haze that changes with stellar activity. The first images may not simply answer whether other Earths exist. They may show us how un-Earth-like a habitable world can be. The colours would be especially fascinating and also especially treacherous. A blue planet is not automatically Earth-like. A pale blue dot could be dominated by atmosphere rather than ocean. A reddish planet might be dry rock, haze, vegetation under a red star, or minerals. A greenish tint might be biology, but it could also be chemistry or scattering. White could be ice, cloud, salt, or something else. Human eyes evolved under our sun, on our planet, for practical tasks like finding fruit, reading faces, and noticing when the toast is becoming smoke. They did not evolve to interpret false colour or reconstructed images of exoplanets around other stars. Science would have to teach our eyes what they are seeing. Spectroscopy would help. A pixel is not just a dot of colour if you can split its light into wavelengths. Spatially resolved spectroscopy, even at coarse resolution, could reveal whether different regions have different compositions. One region might show signs of water absorption. Another might be more reflective in ways consistent with ice. Seasonal changes in atmospheric gases might hint at active cycles. If oxygen, methane, carbon dioxide, water vapour or other molecules are present, their distribution and changes could help interpret the image. The most powerful result would not be a picture alone, but a picture connected to chemistry. A map that says not only bright and dark, but wet, icy, cloudy, warm, dry, changing. Seeing continents and oceans would also let scientists study rotation. As the planet spins, features come in and out of view. If the same dark region appears at regular intervals, the rotation period can be measured. If cloud patterns move differently from surface features, winds can be inferred. If one hemisphere is consistently brighter, that might reveal surface asymmetry or cloud behaviour. Rotation is a basic fact about a planet, but it connects to climate, magnetic fields, atmospheric dynamics, and habitability. A day length of 10 hours creates different circulation than a day length of 30 days. A tidally locked planet may have no ordinary day-night cycle at all. An image over time turns rotation from a number into visible motion. The planet's phase would matter too. Like the Moon, an exoplanet can show different illuminated portions depending on its position around its star. At full phase, more of the day side is visible. At crescent phase, less of the day side is visible, but ocean glint might become stronger under certain conditions. Different phases reveal different scattering behaviour. Clouds, oceans, and atmospheres reflect light in distinct ways as the angle changes. A solar gravitational lens mission might not be able to observe every phase easily, depending on geometry and timing, but phase information would be valuable. It is another reminder that planets are not flat pictures. They are spheres moving through light. There is an emotional danger in imagining the first alien continents. Humans love to name things. We would be tempted to name bright patches, dark basins, possible seas, possible ice caps. Names help us remember, but they can also make distant things feel possessed. A planet around another star would not belong to us because we mapped it. Its mountains, if it has mountains, are not ours. Its oceans, if it has oceans, are not waiting for our flags. Seeing should not automatically become claiming. Astronomy at its best is an act of attention, not ownership. The first exoplanet maps may teach us humility as much as knowledge. Here is a world, they may say. It has been here all along, complete without us. That thought is important if the planet shows signs of life. A living exoplanet would be one of the most precious discoveries imaginable, but also one we could not visit easily, perhaps not for centuries, perhaps not ever. It would be alive at a distance. We would know it through light. Its ecosystems, if any, would remain hidden beyond the resolution of our images. We might see seasonal colour changes or atmospheric gases. We might infer biospheres. But we would not know the texture of its ground, the sound of its weather, the shape of its living things, or whether anything there has ever wondered about the stars. The image would be intimate and distant at the same time, a face glimpsed across an ocean too wide to cross. The idea of city lights sharpens that feeling even more. If we ever saw evidence of technology, the distance would become almost painful. There might be minds there, but no easy way to speak. A message would take years to arrive and years to return, even for the nearest stars. The image itself would already be old, because light takes time to travel. We would not be seeing the planet as it is now, but as it was when those photons left. For Proxima Centauri b, that would be just over 4 years ago, which is almost current by astronomical standards. For a planet 30 light-years away, it would be 30 years ago. The farther the target, the older the image. The first alien city light, if such a thing were ever detected, might be a light from another decade or another century. Astronomy always introduces us to the past. Even without cities, the first resolved image of a habitable candidate would likely become one of the most viewed images in history. People would stare at it not only for what it shows, but for what it means. Some would want it to prove life. Some would want it to be Earth-like. Some would be disappointed if it is cloudy or barren. Some would find even a dry rock magnificent. Scientists would remind everyone about uncertainties. Artists would make versions. Schools would show it. News anchors would point at bright and dark patches. Someone would ask whether we can go there, and someone else would have to explain gently that going there is a much harder problem, and perhaps not tonight. The first image may also change how we see Earth. Every time we observe another world in detail, we understand our own better. Venus taught us about runaway greenhouse conditions. Mars taught us about atmospheric loss and planetary change. The outer moons taught us that oceans can hide under ice. Exoplanets may teach us which parts of Earth are common and which are rare. If many rocky planets have oceans, Earth may feel less lonely. If few do, it may feel more precious. If some have clouds and continents but no life, we may learn that habitability is not the same as inhabited. If life signs appear in several places, biology may become a cosmic process rather than a local miracle. Each possibility changes the story. The sun's gravitational lens would not answer everything. It would not send back smells, sounds, samples, or direct contact. It would not show the small details that make a place feel lived in, but it could give us the first planetary geography beyond the solar system. Geography is a powerful thing. Once you can map a world, you can ask better questions. Where are the oceans? How does the atmosphere move? Does ice form at the poles? Does the surface change with seasons? Are there stable regions that might be habitable? Do the colours suggest chemistry, minerals, or biology? Does the night side glow? The map becomes a framework for all future questions. This is why the dream of seeing oceans, clouds, ice caps, continents, and maybe cities is not only a dream of better pictures, it is a dream of better understanding. It takes the universe from a catalogue of distant objects to a set of places. It makes exoplanets less like entries and more like worlds with weather and history. It reminds us that when we say planet, we are not naming a dot. We are naming a whole physical reality, with light falling across it, with heat moving through it, with surfaces changing under an alien sky. And once we've seen one such world, we will want to see another. That is simply how curiosity behaves. One map will lead to 10 questions. 10 questions will lead to new missions. If one planet has oceans, we will ask how common oceans are. If one has ice caps, we will ask how climates differ around different stars. If one has a strange atmospheric pattern, we will ask whether it is rare or typical. If one shows possible signs of life, we will look for confirmation and comparison. The first resolved exoplanet image would not satisfy the search. It would make the search more serious. For now, all of this waits inside faint light. The oceans, if they exist, are unresolved. The continents, if they exist, are folded into a dot. The clouds are blended with everything else. The ice caps are hidden in the planet's overall brightness. The possible cities, if any exist at all, are far beyond our current reach. But the photons are still travelling. Some of them may pass near the sun. Some may bend slightly through the curved space-time our star creates. One day, a spacecraft may wait in the right darkness and catch enough of them to begin rebuilding the scene. Pixel by pixel, caution by caution, the face of another world may appear. After imagining oceans, clouds, ice caps, continents, and perhaps the faintest possible hints of technology on another world, the idea of the sun as a telescope begins to widen again. At first, we wanted to see. That was the simple dream. We wanted to take a planet that was only a point of light and turn it into a world with shape, weather, and geography. But once you accept that the sun's gravity can focus light, another possibility steps quietly into view. If light can be focused for seeing, then signals can be focused for speaking. The same curved space-time that might help us image a distant exoplanet could also help us send and receive messages across interstellar distances. The sun might not only become the greatest telescope ever built, it might one day become part of the greatest communication system ever imagined. That phrase, communication system, sounds very practical compared with the rest of this story. It brings to mind antennas, transmitters, error correction, signal strength, bandwidth, and perhaps someone in a control room asking why the connection has dropped again. But at interstellar distances, communication becomes almost as grand and difficult as exploration itself. Sending a spacecraft to another star would be an enormous achievement, but speaking with it afterward would be another problem entirely. Space is vast, signals spread out, power is limited, antennas can only be so large. A message sent from a small probe near another star would arrive at Earth as something unbelievably faint, a whisper stretched across light years. We already know how hard it is to communicate with spacecraft in our own solar system, and those are practically next door by comparison. A probe around Alpha Centauri would not be next door. It would be across a cosmic ocean. Radio waves and laser signals both travel at the speed of light, but they still weaken with distance. If you shine a flashlight at a wall nearby, it makes a bright spot. Shine it at something far away, and the beam spreads. By the time a signal crosses light years, even a well-aimed beam can become faint and difficult to detect. To communicate across interstellar distances, you need power, precision, large receivers, good timing, and patience. You also need to accept that a conversation with even the nearest star would not be quick. A message to Proxima Centauri would take a little more than 4 years to arrive, and a reply would take the same time coming back. That is not a phone call. That is more like writing to someone across history and hoping their grandchildren check the mailbox. Now, add the solar gravitational lens. If a spacecraft sits far out along the right line behind the sun's gravity can amplify incoming electromagnetic waves from a distant source. It can also, in some concepts, help focus outgoing signals. The sun becomes a kind of enormous natural antenna, or perhaps more accurately, a gravitational amplifier. The same region that is useful for imaging could be useful for communication. The spacecraft does not need to carry a dish the size of a city. It can use the sun's gravitational field as part of the receiving system. This is the heart of the stellar relay idea. Instead of relying only on artificial hardware, a civilization places communication nodes near the gravitational focal regions of stars, using the stars themselves to boost signals. There is something very sensible about that, once the strangeness wears off. Civilizations that travel between stars would face the same basic problem everywhere. Interstellar distances are too large for casual communication. If you spread probes, colonies, observatories, or scientific stations among nearby stars, you need a way to keep contact. You can build bigger antennas, you can use lasers, you can increase power, but every option costs mass, energy, and engineering effort. If nature already provides massive gravitational lenses around every star, a clever civilization might use them. Every star becomes not just a place of warmth and planets, but a possible node in a communication network. A star is no longer only something you orbit. It is something you align with. This is where the phrase galactic internet appears. It is a dramatic phrase, and we should treat it gently. It does not mean the Milky Way is full of little Wi-Fi routers blinking politely beside every star. It does not mean aliens are streaming sleepy astronomy videos through the sun, although one hopes they would choose a good thumbnail. It means that, in principle, stars could be used as gravitational signal boosters, forming long-distance communication links across space. A probe near the sun's gravitational focus could communicate with another probe near the gravitational focus of another star. The two stars would act as natural amplifiers on both ends of the link. The alignment would need to be extremely precise, but the potential power savings could be enormous. Imagine, for example, a future human probe in the Alpha Centauri system. The probe wants to send data home, images of planets, measurements of atmospheres, perhaps maps of moons or dust belts. Without help, the signal must cross more than 4 light-years and still be detectable by Earth. That is hard. But if the probe can send its signal toward the gravitational focal region of Alpha Centauri, and if another relay near our Sun's focal region is aligned to receive it, the stars themselves may help concentrate the signal. The communication link becomes a bridge made from geometry. Not a physical bridge, of course. No one is strolling across it with luggage. It is a radio or optical bridge, a path of focused electromagnetic energy shaped by gravity. The alignment is the difficult part. A gravitational relay is not like broadcasting in all directions and hoping someone notices. It is more like whispering through a very long, very narrow tube. If you are lined up correctly, the whisper carries. If you're off to the side, you hear almost nothing. A relay spacecraft would need to maintain position along the focal line for the target star or receiver. Stars move, planets tug on stars, spacecraft drift. The sun itself wobbles slightly because the planets pull on it, especially Jupiter. Over long timescales, these motions matter. A relay station would have to correct its position and keep the alignment. This is not impossible, but it is work. The galactic internet, if it ever exists, would not be casual. It would be a network of patient machines constantly trimming their place in the dark. The idea also changes how we imagine the outer solar system. In earlier parts of this journey, the distant hundreds of astronomical units became the place where we might image exoplanets. Now those regions become communication outposts as well. One line from the Sun points opposite Proxima Centauri. Another points opposite Barnard's star. Another toward Tau Ceti, Sirius, or any other target. Each line could, in principle, host a relay spacecraft. If humanity ever sends probes to many nearby stars, the Sun's distant gravitational focal regions might become a kind of communication harbour. Not a single place, but many directions, many lines, many tiny stations spread far beyond the planets, each holding a specific relationship between the Sun and another star. There is a quiet poetry in that, though let's keep it practical enough not to float away. The solar system's edge would no longer be empty in our maps. It would be filled with purpose. Here is the line for Alpha Centauri. Here is the line for Barnard's star. Here is the line for a promising planet around a red dwarf. Here is a relay waiting for a probe that left decades ago. Here is another waiting to send a compressed image archive back toward Earth. The outer darkness becomes infrastructure. The places we once thought of as remote and useless become valuable because they offer the right geometry. A future network might begin with science rather than society. Before any human settlement around another star, if such a thing ever becomes possible, there may be robotic probes. Interstellar probes are likely to be small, fast, and limited in power. If they reach another star and gather data, sending that data home will be one of their hardest jobs. Stellar gravitational relays could help. A probe entering another star system might deploy or work with a relay near that star's focal region. Or perhaps a larger mission architecture would send communication craft separately, building the network before the main explorers arrive. This sounds elaborate, and it is, but interstellar exploration will be elaborate by nature. Once distances are measured in light years, simplicity becomes a luxury. There is also a SETI angle, and it is one of the more intriguing parts of the idea. If gravitational lens communication is useful, then perhaps other civilizations, if they exist and are technologically advanced, might use it too. That raises the question of whether we should look for artifacts or signals near our own sun's gravitational focal lines. A civilization trying to communicate with the solar system might place a relay along the line from its star through the sun, or send tightly focused signals that pass through the solar gravitational lens. Such signals would not necessarily look like broad broadcasts. They might be narrow directed and easy to miss unless we are in the right place or looking in the right direction. This is one reason some researchers have suggested thinking about stellar relays in the context of artifact SETI, the search not only for signals but for possible technological objects. We should be careful here too. There is no evidence that such a network exists. The idea is speculative. It is built on real physics, but the presence of alien relay stations is not something we can assume. The galaxy may be quiet because civilizations are rare, or because communication is hard, or because we are not looking in the right way, or because the timescales do not overlap, or because the universe has a sense of privacy. The stellar relay idea does not solve the mystery of silence. It adds another possible search strategy. It says that if someone were trying to communicate efficiently over interstellar distances, gravitational lens lines might be interesting places to examine. In a human future, the network might grow slowly. One relay near the Sun, then one near another star, perhaps delivered by an interstellar probe, then another link, then a chain. The galaxy is far too large for quick connections, even with perfect signal boosting. Light still sets the speed limit. A message from one side of the Milky Way to the other would take tens of thousands of years. A galactic internet would not feel like the internet we know, where a message crosses the planet almost instantly, and a person can become annoyed if a video takes 3 seconds to load. It would be a slow internet, a deep time internet, a network where nearby stars exchange messages over years, distant regions over centuries or millennia, and the idea of real time becomes almost meaningless. But slowness does not make it useless. Human civilization already preserves messages across long periods. Books speak across centuries. Fossils speak across millions of years. The cosmic microwave background speaks across nearly the age of the universe. A galactic communication network would be slow, but it could still carry maps, science, warnings, histories, genetic archives, art, or simple announcements that a civilization exists. It might not support casual conversation across the galaxy, but it could support memory. It could allow separated communities, probes, or observatories to share knowledge on the timescale of stars. A stellar relay network would also require trust in automation. Machines would need to hold alignment, correct drift, manage power, process signals, and relay messages without constant human attention. In the deep future, some relay stations might operate for centuries. They would need maintenance, replacement, or self-sufficiency. They might be powered by nuclear systems, beamed energy, or perhaps other technologies. They would need to survive dust impacts, radiation, temperature extremes, and the long boredom of space. It is one thing to build a router for a living room. It is another to build one that sits 700 astronomical units from the sun and keeps listening for a signal from another star for 200 years. Though, to be fair, some living room routers also seem to require impossible patience. The beauty of the concept is that it turns stars into shared tools. A civilization does not have to build the largest possible antenna from scratch every time. It can place modest equipment where nature provides amplification. That is similar to the telescope idea. The spacecraft does not need to be enormous because the sun provides the lens. A relay does not need to produce impossible power because the star's gravitational field helps focus the signal. In both cases, the lesson is the same. Advanced spacefaring may depend not only on bigger machines, but on better positions. Knowing where to stand becomes as important as knowing what to build. There is a kind of cosmic thrift in that. Use what is already there. Use a planet's gravity for a slingshot. Use sunlight for a sail. Use a star's gravity for a lens. Use the quiet outer solar system as a platform. Space exploration often looks like conquest in old language, but in practice it is more like negotiation. You cannot command the universe. You learn its rules and then work with them. The sun will not move its focal line closer for us. It will not dim its corona because our detector is sensitive. It will not hold still because our relay prefers it. We adapt to the geometry. We become students of the possible. If the sun becomes part of a galactic internet, the first users may not be humans chatting with other humans around another star. They may be machines, probes sending data, observatories coordinating measurements, relays passing compressed packets across light years. A future exoplanet imaging mission might use one focal region as a telescope and another as a communication link. A probe that maps a planet around another star might send its data back through that star's gravitational lens toward a receiver using the sun's lens. The telescope and the network become connected. Seeing and speaking become two sides of the same gravitational technology. This also means that the first steps towards such a network may come from the same technologies needed for the Solar Gravitational Lens Telescope. Fast travel to hundreds of astronomical units, durable small spacecraft, precise navigation, coronagraphs or optical systems, powerful communication methods, autonomy, and long-lived power. The path to imaging alien worlds may also lay the path to communicating across interstellar space. One mission teaches us to reach the focal line, another teaches us to operate there, another teaches us to transmit and receive efficiently. Slowly the impossible becomes a set of engineering problems, and then a set of test missions, and then maybe one day a quiet piece of infrastructure no one finds surprising anymore. It is worth remembering how strange ordinary technology would look to the past. A person from a few centuries ago might find a smartphone almost magical, a small glowing rectangle that can show maps, send voices across oceans, store libraries, photograph the moon, and also distract you from finding your keys. Yet every part of it depends on natural laws patiently understood and engineered. A galactic internet built on stellar gravitational lenses would feel magical to us now, but to a future civilization, it might simply be the sensible way to keep in touch across stars. Not easy, not instant, not cheap, but sensible. The first relay would probably feel less glamorous than the idea suggests. A small spacecraft, far from the sun, listening. Another small spacecraft, perhaps near another star, transmitting. Years of testing, weak signals, calibration, alignment errors, corrections, long waits. Then one day a message arrives with better efficiency than expected. A link is proven. The sun has become not only a telescope but an antenna made from gravity. The first message might not be grand. It might be a test pattern, a sequence of bits, a timing signal, a scientific packet. History often begins with practical little messages. The first words over a new channel are rarely as poetic as people hope. Sometimes the universe opens a door and the first thing through it is basically, "Can you hear me? Can you hear me?" That might be the deepest question in the galactic internet idea. It is not only about our probes, it is about whether intelligence, if it arises elsewhere, can become connected across the distances that separate stars. Planets may be common, life may or may not be common, technology may be rare, brief, or fragile. But if civilizations learn to use their stars as lenses and relays, then perhaps the galaxy has pathways we have barely begun to imagine. Not highways, not shortcuts. Light still takes its time, but pathways of signal, memory, and observation. Threads between suns. For now, this remains a future dream built from present physics. We have not placed a relay at the sun's gravitational focus. We have not imaged an exoplanet through the solar lens. We have not sent a probe to another star and waited for its data to return through a stellar bridge. But the ideas are connected. They arise from Einstein's strange gift, from the bending of light by gravity, from the recognition that stars are not only lights in the sky, but tools in space-time. The sun as telescope leads naturally to the sun as receiver, transmitter, and node. And once we see that, the story grows larger than one exoplanet image. It becomes a story about a civilization learning how to use its star, not consume it, not control it, not move it, but cooperate with its gravity. First, we use the sun to see another world. Then perhaps we use it to speak across the dark. The little probes far beyond the planets become eyes and ears. The focal lines become corridors of information. The outer solar system becomes less like an edge and more like the beginning of a network. And behind all of this sits the oldest question of the night. If we can use the sun to look and listen so deeply, what might it finally reveal about whether life exists elsewhere in the universe? By the time the sun becomes both a telescope and a possible communication tool in our imagination, the question of life begins to feel closer, even if the stars themselves remain far away. That is the great emotional pull of this whole idea. It is not only about sharper pictures, it is not only about clever spacecraft, gravitational focal lines, solar sails, Einstein rings, or signal relays in the dark. All of those matter, and each one is fascinating in its own right. But underneath them is a quieter hope. We want to know whether Earth is alone in being alive. We want to know whether oceans elsewhere stay empty, whether clouds drift over lifeless stone, whether chemistry becomes biology under other suns, whether intelligence ever looks back, and whether the galaxy is silent because no one is there, or because we have not yet learned how to listen properly. The sun's gravitational lens could become one of the most powerful tools for approaching that question. Not because it would instantly reveal alien creatures, and not because it would turn distant planets into nearby destinations. It would not show us forests in detail, or animals moving across plains, or people in cities if such things exist. It would not let us hear waves breaking on an alien shore or smell rain in another atmosphere. But it could do something that no ordinary telescope can easily do. It could help us see exoplanets as worlds, and that is a major step in the search for life. Life does not exist in a catalogue entry. It exists in environments. It needs energy, chemistry, stability or adaptability, and some kind of physical setting where complex processes can persist. To understand life, we need to understand planets. Today, much of the search for life beyond Earth depends on indirect clues. We look for planets in habitable zones, the regions around stars where liquid water could exist on a planet's surface, if the atmosphere is suitable. That phrase is already full of caution. Could exist, if the atmosphere is suitable. A planet in the habitable zone might be warm enough for water, but it might have no water. It might have too much atmosphere and become a furnace like Venus. It might have too little atmosphere and freeze like Mars. It might be battered by stellar flares. It might be tidally locked. It might have oceans hidden under ice. It might have life underground while looking barren from space. The habitable zone is not a guarantee. It is a place to begin looking. We also search for biosignatures, signs in a planet's atmosphere or surface that could suggest life. Oxygen is often discussed because Earth's oxygen-rich atmosphere is maintained by life, especially photosynthesis. Ozone can be related to oxygen. Methane is interesting because it can be produced by life, though also by geology. Water vapour matters because life as we know it needs water. Carbon dioxide tells us about climate and atmospheric composition. Combinations of gases can be more meaningful than a single gas alone. Oxygen and methane together, for example, can suggest a chemical imbalance that may require ongoing replenishment. But even biosignatures are tricky. Nature has non-living ways to produce some gases. Different planets can fool us. Stars can alter atmospheric chemistry. A promising signal is not always proof. The universe has never signed a contract promising to make life easy to detect. That is why images matter. If we could resolve the surface of a planet even roughly, we could place atmospheric clues in context. Suppose a planet shows water vapour and a climate that might allow liquid water. A solar gravitational lens image might reveal whether it has ocean-like regions. Suppose a spectrum suggests oxygen. An image might show clouds, surface patterns, seasonal changes, or ice. Suppose methane appears. A map might help distinguish a globally volcanic planet from one with ocean-land cycles or seasonal surface changes. No image alone proves life, and no spectrum alone always proves life, but together they become stronger. The sun's lens could help turn scattered clues into a planetary story. The first great revelation might be that potentially habitable planets are physically diverse. We often speak of Earth-like worlds, but Earth-like can hide many assumptions. Earth has a particular size, atmosphere, ocean fraction, rotation rate, moon, magnetic field, plate tectonics, land distribution, biological history and relationship with the sun. A planet can be Earth-sized and still not Earth-like in any meaningful way. It can orbit in the habitable zone and still be dry, frozen, cloudy, toxic or unstable. Or it can be very different from Earth and still habitable in some region. The solar gravitational lens could show us which possibilities are real. It could reveal water worlds, desert worlds, ice-edged worlds, cloudy worlds, tidally locked worlds with permanent twilight zones, and perhaps planets where life survives in ways that do not fit our expectations. That may be one of the most important lessons. The search for life is not only the search for another Earth, it is the search for life's range. Earth is our only example of a living planet, so of course we begin there. We look for water because life here needs water. We look for carbon chemistry because life here is carbon-based. We look for atmospheric imbalance because life here changes the air. But we must be careful not to mistake our starting point for the final answer. The universe may produce living worlds that are recognizably similar to Earth, and it may produce living worlds that are not. A high-resolution image of another planet might help us break out of our local habits. It might show that habitable does not always look blue and green under a yellow sun. If the first planet imaged by the sun's lens turns out to be lifeless, that would still be valuable. In fact, it might be one of the most useful results possible. A planet in the habitable zone with no obvious signs of life would teach us about false hopes and planetary difficulty. Perhaps it lost its atmosphere. Perhaps it has water but no life. Perhaps it is too cloudy to assess. Perhaps it has a stable climate but no biosignature gases. Each outcome would refine the search. Science grows not only from confirmations but from disappointments that are understood clearly. A barren world in the right place would remind us that habitability is a set of conditions, not a promise. If the first image shows an ocean but no biosignatures, the question deepens. Is the ocean sterile? Is life present but not globally detectable? Is the atmosphere hiding evidence? If the planet has a thick ice shell, could life exist beneath it as we wonder about Europa or Enceladus in our own solar system? Remote images are powerful, but they cannot answer every question. Life can be subtle. Microbes can transform a planet over time, but they may also remain hidden in places where surface imaging cannot see them. A world may be alive in the dark, under ice or underground, and from far away it might look quiet. The sun's telescope would expand our vision, not make us omniscient. If, however, the sun's lens helps reveal a planet with strong biosignature gases, surface water, active clouds, seasonal changes, and perhaps surface reflectance patterns that behave in ways suggestive of biology, then the search would change forever. We would not necessarily have proof in the courtroom sense, but we might have a case so strong that the scientific world shifts. The first likely living planet beyond the solar system would become a central object of study for generations. Every telescope would look at it. Every model would be tested against it. New missions would be proposed. Philosophers, theologians, artists, teachers, and ordinary people trying to fall asleep would all have something new to think about. The night sky would no longer be only full of possible life. It would contain a named world where life may actually be happening. What would that do to us? Not in a dramatic instant, perhaps. Humans are surprisingly good at turning cosmic revelations into everyday facts. We learned that Earth orbits the Sun, that the Sun is one star among billions, that the Milky Way is one galaxy among countless galaxies, that planets are common, that the universe is expanding, and still someone must remember to buy milk. Life goes on. But underneath daily life, our sense of place changes. The first strong evidence for life on an exoplanet would be one of those changes. It would not make Earth less important. It might make Earth more important, because we would understand it as one living example in a larger cosmic pattern. A single flame is precious in darkness. Two flames tell you fire can spread. The image of a living world would also reshape the Fermi question, the old puzzle of why, if life or intelligence is common, we have not clearly encountered it. If we find simple life, but no technology, perhaps life is common and intelligence is rare. If we find many habitable planets but no biosignatures, perhaps life is difficult to start. If we find biosignatures on multiple worlds, the galaxy may be biologically rich, but technologically quiet. If we ever find technosignatures, then the question changes again. The sun's gravitational lens cannot solve all of this alone, but it could provide a new kind of evidence. Not just a signal from somewhere, not just a molecule in an atmosphere, but a planet seen in context. The possibility of cities, artificial lights, or technological patterns remains the most speculative and the most emotionally charged. It is also the one that requires the strongest caution. A strange light pattern is not automatically a city. A chemical imbalance is not automatically industry. A repeating signal is not automatically a greeting. We must be willing to be excited and skeptical at the same time, which is a difficult but necessary scientific posture. It is like leaning forward while keeping your feet firmly on the floor. If the sun's lens ever helps detect a possible technosignature, the first years afterward may be full of uncertainty. The most important work would be ruling out natural explanations. Only after every ordinary explanation fails should extraordinary ones be allowed to stand. If an alien civilization were detected even indirectly, the distance would become part of the meaning. We would not be neighbours in the usual sense. We would be separated by years, perhaps decades or centuries of light travel time. Any image would be old, any message would be slower than a lifetime if the world is far enough away. Contact, if it ever occurred, might be generational. The sun's lens might show us that someone is there, while also reminding us how far away there really is. That combination of closeness and distance is deeply strange. To see evidence of minds and yet not be able to speak quickly would make the universe feel both less lonely and more vast. Even if no life is found at first, the sun's telescope could reveal how rare Earth's combination of features is. We might discover many planets with one ingredient but not the full recipe. Oceans without oxygen, atmospheres without stability, clouds without surfaces, surfaces without water, habitable zones without habitability. Or we might find planets that surprise us entirely, worlds with unexpected climates, strange reflective surfaces, or atmospheric cycles that do not resemble any solar system example. Each one would teach us what planets can become. Life is part of planetary science, but planetary science is larger than the search for life. To understand life, we must first understand the stage on which it might appear. There's also a lesson about patience in the search for life. A solar gravitational lens mission would take decades to launch, travel, operate, and interpret. The results would not come quickly. They would arrive after long planning, long silence, long communication delays, and careful reconstruction. This pace might be frustrating in a world used to instant images and constant updates, but it is appropriate for the question. Life in the universe is not a small question. It does not owe us a quick answer. We have spent thousands of years wondering whether the stars are suns, whether other worlds exist, whether anything lives there. If the answer takes another century to sharpen, that is still fast by the standards of stars. The sun itself gives this patience a physical form. It has been shining for billions of years. It bent light before life crawled onto land. It bent light before humans made language. It bent light while the first telescopes were being polished, while Einstein wrote equations, while rockets first climbed into the sky, while exoplanets were discovered one by one. The lens has been there the whole time. We are the new part of the story. Our understanding is young. Our spacecraft are young. Our desire to use the sun as a telescope is a recent thought in the long life of a star. There is something calming about that. The opportunity is not rushing past us. It waits in the geometry. What might the sun's greatest telescope reveal then? It might reveal a planet with wide oceans under a red sky. It might reveal a dry world that once seemed promising but has no air. It might reveal a planet wrapped so completely in clouds that its surface remains hidden. It might reveal polar ice, storm belts, seasonal snow, desert continents, ocean glints, or a permanent dayside cloud shield. It might reveal that Proxima Centauri b, or some other nearby world, is less Earth-like than hope suggested, or more interesting than anyone expected. It might reveal the first strong evidence that biology has changed another planet's atmosphere. It might reveal nothing alive at first, but enough worlds to show us where to look next. That last possibility matters. The first mission does not have to find life to be transformative. If it proves that the sun's gravitational lens can image exoplanets, then it creates a method. Methods are often more important than single results. Galileo's telescope did not only show moons around Jupiter, it opened telescopic astronomy. Spectroscopy did not only identify one element, it opened chemical astronomy. Gravitational wave detectors did not only detect one merger, they opened a new way of listening to the universe. A successful solar gravitational lens mission would open resolved exoplanet imaging. It would say, we can do this. We can turn nearby exoplanets into maps. After that, the search expands. Future generations might look back at the first solar gravitational lens image the way we look at the first blurry photographs of Mars or the first grainy view of Earth from space. Technically limited, emotionally enormous. Later images may be better. Later missions may image many worlds. The first one may look rough compared with what comes after, but the first one will carry the shock of transition. Before it, exoplanets were mostly hidden. After it, at least one had a face. That is the kind of boundary humans remember. The deeper transformation may be internal. Seeing another world clearly may change how we think about home. Earth is not precious because it is the only planet. It is precious because it is the one that holds us, the one where life has made a breathable atmosphere, the one where oceans and continents and clouds and ice have carried a long biological story. If we find other living worlds, Earth becomes part of a family. If we do not, Earth becomes even more rare in our knowledge. Either way, the view from the sun's telescope turns back toward us. Every search outward eventually does. There is a gentle irony in using the sun to ask whether life exists elsewhere. The sun is the reason Earth is alive in the way it is. Its light drives our climate and food webs. Its gravity holds us in orbit. Its stability gave life time. And now, if we become skilled enough, its gravity may help us study the living possibilities around other stars. Our star may become the instrument through which we learn whether other stars have living worlds of their own. The sun would not answer in words. It would answer by bending light. And so, the story settles into a final image. A small spacecraft waits far beyond the planets, perhaps hundreds of astronomical units from the warmth of Earth. Behind it lies the deep outer solar system. Ahead of it, from its point of view, is the sun, bright and carefully blocked by its instrument. Around the hidden solar disk, a faint ring of light trembles with information from another world. The spacecraft measures. Earth listens. Computers reconstruct. Scientists check, doubt, improve, and check again. Slowly a planet appears. Maybe blue, maybe rust red, maybe white with clouds, maybe dark with oceans, maybe strange in ways our words are not ready for. Somewhere in that image may be the answer to a question older than astronomy itself. Are we alone? Maybe the answer will be yes, at least for a while. Maybe it will be no, but quietly, with microbes beneath clouds or oceans under ice. Maybe it will be no in a way that changes every future conversation humanity has about itself. We cannot know yet. But the path toward knowing may begin with something we already have. A star, gravity, light, and the willingness to send tiny machines into the dark so that our vision can grow larger than our bodies. For tonight, that is enough to rest with. The sun, outside your window or hidden on the far side of Earth while you listen, is not only the lamp of our days, it is a lens waiting in space. It is a possible bridge. It is a reminder that the universe sometimes hides its greatest instruments in plain sight. We looked at the sun for warmth, then for calendars, then for physics, then for energy, and perhaps one day we will look through it, using its curved space-time to see the face of another world. And whether that world is alive or silent, familiar or strange, bright with oceans or covered in cloud, it will have sent its light across the dark to meet our star, and through our star to meet us. So as your thoughts begin to slow, you might picture that future ring of light around the sun, thin and faint and full of distance. You might picture the first pixels forming on a screen, not as fantasy, but as the patient result of gravity doing what gravity has always done. Somewhere out there, planets are turning, their clouds are moving, their ice is growing and shrinking, their oceans, if they have oceans, are catching starlight. And here, around our ordinary yellow sun, the shape of space-time may already be holding the beginning of their first true portraits, waiting for us to travel far enough and carefully enough to receive them.